Tonight, we're going to explore something that could explain one of the most disturbing mysteries in all of science: the Great Filter. You've probably heard this term before. Scientists use it when discussing why we haven't found alien civilizations. But here's what most people don't realize. The Great Filter isn't just an abstract concept. It's potentially a cosmic death sentence that has already claimed countless civilizations throughout the universe. Right now, as you're listening to this, we exist in a galaxy containing hundreds of billions of stars, many with planets in the habitable zone where life could flourish. The math suggests the universe should be teeming with intelligent civilizations. Yet when we look up at the night sky, we hear only silence, complete, absolute silence. This silence isn't just puzzling, it's terrifying, because it suggests that somewhere between the first spark of life and becoming a spacefaring civilization, there's a filter so deadly that almost nothing gets through it. And we don't know if it's behind us or waiting ahead. By the end of tonight, you're going to understand why this concept might be the most important idea for humanity's survival, and why our next few centuries could determine whether we join the cosmic graveyard or become one of the rare civilizations that makes it to the stars. Before we dive in, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now let's begin. Imagine for a moment that you could step outside our galaxy and look back at the Milky Way from a distance of millions of light years. What you would see is a magnificent spiral of light containing somewhere between 200 and 400 billion stars, each one a sun in its own right, many of them older than our own solar system by billions of years. This single galaxy of ours is just one among an estimated 2 trillion galaxies in the observable universe, each harboring its own collection of hundreds of billions of stellar fires burning across the cosmic dark. As you contemplate this vast celestial architecture, you might naturally wonder about the worlds that orbit these distant suns. Thanks to revolutionary space telescopes like Kepler, TESS, and the countless ground-based observatories that scan the skies each night, we now know that planets are not rare cosmic accidents, but rather the natural byproducts of star formation. Nearly every star you can see has at least one world orbiting it, and many harbour entire families of planets, some rocky like Earth, others gaseous giants like Jupiter, and still others unlike anything in our own solar neighbourhood. What makes this discovery truly remarkable is how many of these worlds exist in what astronomers call the habitable zone, that narrow band of space around each star where temperatures allow liquid water to exist on a planet's surface. Call it the Goldilocks zone, where conditions are not too hot, not too cold, but just right for the chemistry of life as we understand it. Current estimates suggest that there could be tens of billions of potentially habitable worlds in our galaxy alone, worlds with stable climates, protective atmospheres, and all the basic ingredients necessary for biology to take hold and flourish. When you multiply these numbers across cosmic time, the implications become even more staggering. Our universe is approximately 13.8 billion years old, and the first stars capable of forging the heavy elements necessary for rocky planets and complex chemistry began shining more than 10 billion years ago. This means that countless worlds have had billions of years longer than Earth to develop life, to evolve complexity, and to give rise to intelligence. Some civilizations, if they exist, would have had time to spread across entire star systems, to harness the energy of their suns, and to reach a level of technological development that we can barely imagine. Yet when we turn our most sensitive radio telescopes toward the heavens and listen for any sign of these ancient civilizations, we hear nothing. When we scan the sky for the infrared signatures of massive engineering projects, the kinds of megastructures that an advanced species might build around their star to capture its energy, we find only natural astronomical objects. When we look for the optical flashes of interstellar spacecraft, the atmospheric pollution of industrial worlds, or any of the countless other signatures that a technological civilization might leave in its wake, we discover only silence. This profound quiet was first articulated as a formal paradox in 1950 by the physicist Enrico Fermi during a casual lunch conversation at Los Alamos National Laboratory. While discussing the possibility of extraterrestrial life with his colleagues, Fermi suddenly stopped and asked a question that has haunted scientists ever since. But where is everybody? He had performed a quick mental calculation and realized that even with conservative assumptions about the rate of technological development and space travel, any civilization that had achieved interstellar flight should have been able to colonize the entire galaxy within a few million years, a blink of an eye in cosmic terms. The mathematics of Fermi's insight are unsettling when you work through them carefully. If intelligent life arose even occasionally throughout the galaxy's history, and if just a small percentage of those civilizations developed space travel and chose to expand beyond their home worlds, then by now every star system, including our own, should show evidence of their presence. Yet we see nothing. We detect no artificial radio signals, no signs of stellar engineering, no evidence of the massive industrial infrastructure that a galaxy-spanning civilization would require. This absence of evidence becomes even more puzzling when you consider how young our own civilization is by galactic standards. Modern humans have existed for only about 300,000 years, and we have possessed radio technology for barely more than a century. We have been actively searching for extraterrestrial intelligence for only about 60 years, using increasingly sophisticated methods and instruments. From a cosmic perspective, we have just begun to look and listen, yet already the silence seems deeper and more complete than our theories would predict. Some scientists have suggested that we simply haven't been looking long enough or with sufficient sensitivity to detect other civilizations. Perhaps alien signals are there, but they use communication methods we haven't yet imagined, or they operate on frequencies we haven't thought to monitor. Perhaps they have deliberately chosen to avoid contact with younger species like ourselves, maintaining a kind of cosmic quarantine until we prove ourselves worthy of joining a galactic community. These possibilities offer some comfort, but they struggle to explain the total absence of any detectable signs of intelligence across billions of years of cosmic history. The silence extends beyond just radio signals or intentional communications. A truly advanced civilization would likely undertake massive engineering projects that would be visible across interstellar distances. They might build structures around their stars to capture energy, construct vast habitats in space, or even move entire star systems to more favorable locations. The waste heat from such megaprojects would glow in the infrared, creating signatures that our space-based telescopes should easily detect. Yet comprehensive surveys of nearby galaxies have found no evidence of such large-scale engineering, no signs of the cosmic construction projects that we might expect from billion-year-old civilizations. As you contemplate this cosmic quiet, you begin to understand why it feels so unsettling. We are like explorers who have discovered what appears to be a vast, fertile continent, perfectly suited for habitation, yet completely empty of the cities and civilizations we expected to find there. The silence suggests that something fundamental may be missing from our understanding of how life develops in the universe, or perhaps something profound and disturbing about the fate that awaits technological civilizations. This is the mystery that will guide us through everything that follows, a mystery that may hold the key to understanding not just the cosmos, but our own future among the stars. When you examine the story of life on Earth, one of the most striking facts is how quickly it appeared after our planet became capable of supporting it. Earth formed approximately 4.6 billion years ago from the gravitational collapse of dust and gas in the early solar system, but for its first few hundred million years, it remained a hellish world of molten rock, Constant bombardment by asteroids and comets, and an atmosphere utterly hostile to any form of biology as we know it. The surface was so hot that any water would have immediately boiled away into space, and the early atmosphere likely contained little oxygen but abundant toxic gases that would kill most modern life forms within minutes. Yet remarkably, as soon as conditions on Earth stabilized enough to allow liquid water to persist on the surface, life appeared. The oldest evidence of biological activity dates to at least 3.5 billion years ago, and some researchers argue for signs of life stretching back as far as 4.1 billion years, almost as soon as the planet's crust had cooled and solidified. This timing suggests something profoundly important about the nature of life itself. The transition from sterile chemistry to self-replicating biology may not be the impossibly rare accident that many scientists once believed it to be. Consider what this rapid emergence implies about the fundamental processes that create life. If abiogenesis, the origin of life from non-living matter, required an extraordinary series of nearly impossible coincidences, you would expect it to take much longer to occur, perhaps billions of years of random chemical experimentation before the right combination of molecules finally stumbled upon the secret of self-replication. Instead, life appears to have emerged almost as soon as the basic conditions were met, suggesting that given the right environment and sufficient time, the chemical pathways that lead to biology may be more like rivers flowing downhill than lightning strikes from a clear sky. This observation about Earth's biological timeline becomes even more significant when you place it within the framework that astronomers use to think about life in the universe. In 1961, the astronomer Frank Drake proposed what has become known as the Drake equation, not as a tool for calculating exact numbers, but as a way to organize our thinking about the factors that determine how many communicating civilizations might exist in our galaxy at any given time. The Drake equation breaks down this vast question into a series of more manageable components. It begins with the rate at which new stars form in the galaxy each year, then multiplies this by the fraction of stars that have planetary systems, followed by the average number of planets per star that could potentially support life, then the fraction of those planets where life actually develops, then the fraction where intelligent life evolves, then the fraction that develops technology capable of interstellar communication, and finally the length of time that such civilizations remain detectable to other species like ourselves. When Drake first formulated this framework, most of these terms were complete unknowns, little more than educated guesses based on our single example of Earth and our limited understanding of planetary formation and biological evolution. For decades, scientists could only speculate about whether planets were common or rare, whether habitable worlds existed in significant numbers, or whether the conditions that led to life on Earth were typical or extraordinary throughout the cosmos. However, the past 2 decades have witnessed a revolution in our understanding of several key components of the Drake equation. Space-based observatories like Kepler have monitored hundreds of thousands of stars simultaneously, detecting the tiny dimming that occurs when a planet passes in front of its host star. The Transiting Exoplanet Survey satellite continues this work, scanning the entire sky for planetary transits. Ground-based surveys using radial velocity measurements detect the gravitational wobble that planets induce in their stars. Together, these missions have transformed our knowledge of planetary systems from speculation to measurement. The results have been extraordinary. We now know that planets are not rare cosmic accidents, but rather natural byproducts of star formation. Nearly every star in the galaxy hosts at least one world, and many have multiple planets orbiting them. More importantly, we have discovered that Earth-sized planets in the habitable zones of their stars are remarkably common. Current estimates suggest that roughly 20 to 25% of Sun-like stars have Earth-sized planets receiving similar amounts of energy from their host stars as our own world receives from the Sun. When you apply these measured values to the early terms of the Drake equation, the numbers become compelling. Our galaxy forms approximately 7 new stars each year, nearly all of which will have planetary systems. This means that every year, the Milky Way gains several new potentially habitable worlds, each one a possible cradle for the development of life and intelligence. Over the billions of years that our galaxy has been forming stars and planets, the total number of worlds where life might have emerged runs into the tens of billions. Even if you adopt conservative estimates for the later terms in the equation, assuming that only a small fraction of habitable planets actually develop life, and only a tiny percentage of those evolve intelligence, and only a minuscule proportion of intelligent species develop technology, the mathematics still suggests that our galaxy should host numerous civilizations. Some estimates yield thousands of technological species, others suggest dozens, but very few reasonable sets of assumptions result in Earth being completely alone. This creates what philosophers of science call a tension between theory and observation. The Drake equation, filled in with our best current knowledge of star formation, planetary systems, and the rapid emergence of life on Earth, predicts a universe that should be rich with intelligence and technology. Yet when we search for evidence of these predicted civilizations, we find only silence. The very astronomical surveys that have shown us how common habitable planets are have also revealed how empty the galaxy appears to be of the signatures we might expect from advanced technological societies. This contradiction forces us to confront an uncomfortable possibility. Perhaps one or more of the factors in the Drake equation is far more restrictive than we currently believe. Perhaps there is some step in the long chain from sterile planets to galaxy-spanning civilizations that acts as an almost insurmountable barrier, filtering out the vast majority of potential life before it can announce its presence to the cosmos. The contradiction between what we observe in the universe and what our best theories predict has led scientists to propose one of the most sobering concepts in all of astrobiology, the Great Filter. This idea, first articulated by economist Robin Hanson in 1996, offers a potential resolution to the Fermi Paradox, but it does so in a way that fundamentally challenges our assumptions about life, intelligence, and our own future among the stars. At its core, the Great Filter is not a specific event or phenomenon, but rather a conceptual framework for understanding why advanced civilizations appear to be so extraordinarily rare. The hypothesis suggests that somewhere in the long evolutionary pathway from sterile matter to a galaxy-spanning technological civilization, there exists one or more steps that are so improbable, so difficult to overcome, that they effectively prevent the vast majority of potential life from progressing beyond them. Like a filter that allows only the finest particles to pass through while blocking everything else, this cosmic barrier permits only an infinitesimally small fraction of worlds to develop into the kind of advanced, spacefaring societies that we might be able to detect from across interstellar distances. When you think about the Great Filter, it's important to understand that it could take several different forms. It might be a single, extraordinarily unlikely event, something so improbable that it occurs perhaps once in a trillion worlds, if at all. Alternatively, it could be a series of moderately unlikely steps that, when combined, create an insurmountable barrier. Imagine trying to flip a coin and get heads 10 times in a row. Each individual flip has a 50% chance of success, but the probability of achieving the entire sequence is less than 0.1%. Similarly, even if each step in the evolution from simple chemistry to advanced civilization has a reasonable chance of occurring, the combined probability of successfully navigating all the required transitions might be vanishingly small. The genius of the Great Filter concept lies in its flexibility and its ability to explain the apparent emptiness of the cosmos without requiring us to abandon everything we know about physics, chemistry, and biology. It doesn't suggest that life is impossible or that intelligence cannot evolve. Instead, it proposes that the full sequence of events necessary to create a detectable technological civilization is so demanding that it rarely, if ever, runs to completion. But this explanation for cosmic silence raises a question that may be the most important one our species has ever contemplated. Where exactly does this filter lie in the sequence of evolutionary development? Is it located somewhere in our distant past, representing hurdles that Earth has already successfully navigated? Or does it await us in our future, a trap that has claimed countless other civilizations and now lies in wait for humanity as we continue our technological ascent? If the great filter lies primarily behind us, then we are among the extraordinarily fortunate few who have managed to overcome the most difficult challenges in the evolution of complex life. Perhaps the origin of life itself is far more improbable than Earth's rapid biological emergence suggests. Perhaps the development of complex cells with nuclei and organelles represents a nearly impossible evolutionary leap. Perhaps the emergence of multicellular organisms, the evolution of intelligence, or the development of technology requires such a precise sequence of unlikely events that Earth represents a cosmic miracle, a one-in-a-trillion success story in a universe otherwise dominated by sterile worlds or planets that never progressed beyond simple microbial life. This interpretation of the Great Filter carries with it a sense of profound responsibility and privilege. If most of the universe's difficulty lies behind us, then every human being alive today is part of an almost impossibly rare phenomenon. We would be the universe's way of knowing itself, the cosmos made conscious through a chain of evolutionary accidents so unlikely that they might never be repeated anywhere else in the observable universe. In this view, our continued survival and eventual expansion to other worlds would represent not just a triumph for humanity, but a victory for consciousness itself against the vast indifference of space and time. However, the alternative interpretation is far more unsettling. If the Great Filter lies primarily ahead of us, then the silence of the cosmos becomes an ominous warning rather than a testament to our uniqueness. In this scenario, countless civilizations throughout galactic history have reached approximately our current level of development, with space travel, global communication networks, and the ability to detect and analyze distant worlds. But something systematically prevents these civilizations from progressing much further. Something stops them from becoming the long-lived, galaxy-spanning societies that would be easily detectable by species like ourselves. If this is the case, then the empty sky above us is filled not with absent life, but with the ghosts of failed civilizations. Every star system might once have hosted a technological species that flourished for a few centuries or millennia before encountering some insurmountable challenge that ended their expansion into the cosmos. The Great Filter ahead of us might represent existential risks that we have not yet fully recognized or understood. Challenges that appear with such regularity in the development of technological civilizations that almost none survive to become the ancient, wise species that science fiction has taught us to imagine. This possibility transforms our current moment in history into something far more significant than most people realize. If the Great Filter lies ahead, then the next few centuries may represent the most critical period in not just human history, but in the history of intelligence on Earth. The decisions we make about nuclear weapons, climate change, artificial intelligence, biotechnology, and countless other emerging challenges may determine whether humanity joins the ranks of successful civilizations that pass through the filter, or becomes another silent entry in the cosmic graveyard of failed technological species. The profound uncertainty about where the Great Filter lies creates a unique form of cosmic suspense. We cannot yet know whether we should feel gratitude for having won an impossible lottery or fear at approaching a test that has claimed every other civilization that has attempted it. What we do know is that understanding this concept may be crucial for our species' long-term survival, and that the empty sky above us holds lessons we are only beginning to comprehend. To understand where the great filter might lie, you must first appreciate the extraordinary sequence of cosmic events that had to unfold perfectly for a world like Earth to exist at all. The story begins not with planets, but with the universe itself, emerging from the Big Bang 13.8 billion years ago as a rapidly expanding sphere of pure energy that gradually cooled enough for the first atoms to form. In those earliest moments, the cosmos contained only the lightest elements: hydrogen, helium, and trace amounts of lithium. There was no carbon, no oxygen, no silicon, no iron, none of the heavy elements that form the rocky planets where complex chemistry and life as we know it can develop. For hundreds of millions of years, the universe remained dark, filled with these primordial gases but containing no stars to illuminate the cosmic night. Gravity eventually began to pull the hydrogen and helium together into vast clouds that collapsed under their own weight, igniting nuclear fusion and creating the first generation of stars. These ancient suns were massive, short-lived, and ultimately transformative. Deep within their cores, the immense temperatures and pressures forged new elements through nuclear fusion, building up heavier atoms from lighter ones in a process that continues to power every star you see in the night sky. When these first-generation stars exhausted their nuclear fuel, they died in spectacular, supernova explosions that scattered their newly created elements across space. These stellar deaths were not endings, but beginnings, seeding the universe with carbon, oxygen, silicon, magnesium, iron, and all the other elements necessary for rocky planets and organic chemistry. Each subsequent generation of stars incorporated more of these heavy elements, gradually enriching the galaxy's chemical composition and making planets like Earth possible. This process of cosmic chemical evolution creates what astronomers call the galactic habitable zone, a broad region within our galaxy where conditions are suitable for complex life to develop. Too close to the galactic center, and a planetary system would be bombarded by dangerous radiation from the supermassive black hole that lurks there, along with frequent gamma-ray bursts and supernovae that could sterilize any nearby worlds. The stellar density is also much higher near the galactic core, leading to gravitational interactions that could destabilize planetary orbits or strip planets away from their host stars entirely. Too far from the galactic center, in the outer reaches of the spiral arms, and you encounter a different problem: insufficient metallicity, as astronomers call the abundance of heavy elements. Stars in these remote regions formed from gas clouds that had been enriched by fewer generations of stellar death and rebirth, meaning they contain smaller proportions of the elements necessary for rocky planet formation. Without adequate carbon, silicon, iron, and other heavy elements, you might find only gas giant planets like Jupiter and Saturn, worlds utterly unsuitable for the surface chemistry that appears to be necessary for life. Earth orbits within what appears to be the sweet spot of this galactic habitable zone, roughly 26,000 light-years from the galactic center, in a location where heavy elements are abundant enough to form terrestrial planets, but radiation levels and stellar interactions remain manageable. Yet even this favorable galactic location is only the beginning of the requirements for a truly habitable world. Around each individual star lies another, much smaller habitable zone, often called the Goldilocks zone, after the fairy tale character who sought conditions that were neither too hot nor too cold, but just right. This circumstellar habitable zone represents the narrow range of distances from a star where liquid water can exist on a planet's surface. Too close, and any water would boil away into space, leaving behind a hellish world like Venus with surface temperatures hot enough to melt lead. Too far away, and water would freeze solid, creating a snowball world where biological processes would slow to a crawl or stop entirely. The width of this habitable zone depends critically on the type of star at the system's center. Massive, hot stars burn brightly but briefly, often exhausting their nuclear fuel in just millions of years, far too short a time for complex life to evolve. These stellar giants also emit dangerous levels of ultraviolet radiation that could strip away a planet's atmosphere or damage any organic molecules that might form on its surface. At the other extreme, small red dwarf stars burn for trillions of years, but their habitable zones are so close to the star that planets there would likely become tidally locked, with one side permanently facing the star while the other remains in eternal darkness. Sun-like stars represent a middle ground, burning steadily for billions of years while providing a habitable zone at a comfortable distance where planets can maintain stable, temperate conditions over the vast timescales necessary for biological evolution. Yet even orbiting within this zone is no guarantee of habitability, as the tragic example of Venus demonstrates. Despite receiving only twice as much solar energy as Earth, Venus experienced a runaway greenhouse effect that turned it into an inferno with surface pressures 90 times greater than Earth's and temperatures exceeding 800 degrees Fahrenheit. The rare Earth hypothesis, proposed by paleontologist Peter Ward and astronomer Donald Brownlee, suggests that truly Earth-like conditions may be far more uncommon than the simple concept of habitable zones implies. Their analysis identifies dozens of factors that may be necessary for complex life. A planet must have the right mass to retain its atmosphere without becoming a crushing high-pressure world, the right distance from its star to maintain liquid water, the right orbital characteristics to avoid extreme seasonal variations, and the right composition to support plate tectonics, which appear essential for regulating planetary climate over geological timescales. Earth may also owe its habitability to a series of cosmic accidents that seem almost impossibly fortunate. Our large moon, formed by a giant impact early in Earth's history, helps stabilize our planet's axial tilt and creates tides that may have been crucial for early life. Jupiter acts as a gravitational shield, deflecting many comets and asteroids that might otherwise pummel the inner solar system. Our solar system's location between spiral arms has protected us from the worst of galactic radiation while still providing enough heavy elements for planet formation. When you consider all these requirements together, the formation of a genuinely habitable world begins to look less like a natural consequence of planet formation and more like an extraordinary stroke of cosmic luck, suggesting that part of the great filter may lie in the simple challenge of creating worlds suitable for complex life. Even if a planet possesses all the right conditions for habitability, with liquid water, a stable climate, and protection from cosmic radiation, it still faces perhaps the most mysterious hurdle of all: the transition from sterile chemistry to living biology. This process, known as abiogenesis, represents one of the most profound puzzles in all of science, and many researchers believe it may be where the great filter claims most of its victims. The challenge of creating life from non-life is so complex that despite decades of intensive research and increasingly sophisticated experiments, we still have no clear understanding of how it actually occurs. When you examine the fundamental requirements for life, the magnitude of this challenge becomes apparent. Every living organism on Earth, from the smallest bacteria to the largest whales, is built from the same basic components: complex organic molecules that can store information, catalyze chemical reactions, and create barriers between the living organism and its external environment. These molecules must not only form spontaneously from simpler compounds, but they must also organize themselves into systems capable of metabolism, growth, and most importantly, reproduction. Without the ability to make copies of itself, even the most sophisticated molecular machine would remain forever a chemical curiosity rather than the foundation for biological evolution. The timeline of life's appearance on Earth provides tantalizingly ambiguous clues about how difficult this transition might be. Our planet's surface remained molten and utterly hostile to any form of biology for approximately 600 million years after its formation. Yet as soon as conditions stabilized enough to support liquid water and basic organic chemistry, life appears to have emerged with remarkable speed. The oldest confirmed fossils date to about 3.5 billion years ago, but some researchers argue for evidence of biological activity stretching back as far as 4.1 billion years, which would place the origin of life almost immediately after Earth's crust cooled and solidified. This rapid emergence of life has led some scientists to argue that abiogenesis may not be the impossibly rare accident that many theories suggest. If life required an extraordinary sequence of molecular coincidences, you might expect it to take hundreds of millions or even billions of years of random chemical experimentation before the right combination of molecules finally achieved self-replication. Instead, life seems to have appeared almost as soon as the basic conditions were met, suggesting that given suitable environments and sufficient raw materials, the chemical pathways leading to biology might be relatively straightforward. However, this interpretation faces a subtle but devastating logical challenge known as selection bias. We can only observe and study the universe from planets where life successfully emerged and evolved to produce intelligent observers. This creates a fundamental distortion in our perspective. No matter how improbable abiogenesis actually is, it will always appear to have happened quickly on Earth, because we would not exist to measure its timing on worlds where it failed to occur or took billions of years longer than it did here. Consider this analogy. Imagine that winning a particular lottery requires correctly guessing a sequence of 100 numbers, an event so improbable that it might happen only once in the entire history of the universe. If you were the winner of that lottery, you might look at the timing and conclude that winning must not be very difficult, since it happened to you on your first attempt. But this conclusion would be completely wrong. You would exist to make this observation only because you were the fantastically improbable winner, while countless others who never won would not be around to report their failure. Similarly, the rapid appearance of life on Earth might reflect not the ease of abiogenesis, but rather the fact that we can only observe the outcome from one of the rare worlds where this extraordinarily unlikely process actually succeeded. On countless other planets throughout the galaxy, organic molecules might be endlessly combining and recombining without ever achieving the breakthrough to self-replication, leaving those worlds forever sterile and silent. The challenge of abiogenesis becomes even more daunting when you consider what biochemists call the hard steps theory. This approach suggests that the evolution from simple chemistry to spacefaring civilization requires successfully navigating several distinct transitions, each of which is individually improbable. The origin of life from non-living matter represents just the first of these challenges, followed by the development of more complex cellular structures, the evolution of multicellular organisms, the emergence of intelligence, and the development of advanced technology. Even if each of these steps has a moderate probability of occurring, say 1 chance in 1,000, the combined likelihood of successfully completing all of them becomes vanishingly small. With 5 major transitions each having a 1 in 1,000 probability, the overall chance of producing a technological civilization drops to 1 in a quintillion, a number so small that even a galaxy containing hundreds of billions of stars might expect to see only a handful of successful outcomes over cosmic history. Yet recent research in evolutionary biology and astrobiology has begun to challenge some assumptions underlying these pessimistic calculations. Laboratory experiments have shown that under certain conditions, complex organic molecules can form spontaneously from simpler precursors more readily than previously thought. Some researchers argue that natural selection, rather than being a biological process, is actually a more fundamental principle of chemistry and physics that can drive the organization of non-living systems toward increasing complexity and efficiency. Studies of extremophiles, organisms that thrive in conditions once thought impossible for life, have also expanded our understanding of where biology can flourish. Life has been discovered in boiling hot springs, in waters so acidic they would dissolve metal, in salt concentrations that would kill most organisms, and in environments with no oxygen or sunlight whatsoever. These discoveries suggest that the chemical conditions suitable for life may be far more common throughout the universe than Earth's relatively temperate environment led us to believe. The question of whether abiogenesis represents the great filter remains tantalizingly open. If the transition from chemistry to biology is indeed extraordinarily difficult, then Earth may be one of the few worlds in the galaxy where this hurdle has been successfully overcome, making every living creature on our planet part of an almost impossibly rare phenomenon. Alternatively, abiogenesis might be relatively straightforward given the right conditions, in which case the great filter must lie elsewhere in the long journey from microbes to starships, waiting to challenge civilizations at some later, more vulnerable stage of their development. Even if abiogenesis successfully occurs on a world, creating the first self-replicating molecules that we might call life, that achievement represents only the beginning of an even more daunting evolutionary journey. For most of Earth's biological history, life remained locked in a form that would be invisible to the naked eye, consisting entirely of simple, single-celled organisms that floated in ancient oceans or formed thin films on rocks and sediments. This microbial era dominated our planet for over 2 billion years, an almost incomprehensibly long period during which complex life as we understand it simply did not exist. When you contemplate the vast duration of this microbial age, it becomes clear that the transition from single cells to complex organisms was neither rapid nor inevitable. From approximately 3.8 billion years ago, when the first clear evidence of life appears in the geological record, until roughly 1.5 billion years ago, Earth's biosphere consisted entirely of prokaryotes, bacteria, and archaea lacking the internal compartments and sophisticated molecular machinery that characterize more advanced forms of life. These ancient microorganisms were remarkably successful in their own right, developing photosynthesis, chemosynthesis, and countless other metabolic innovations that continue to power life on Earth today, but they showed no tendency to evolve toward the complexity that would eventually give rise to plants, animals, and intelligence. The breakthrough that finally ended this microbial monopoly was the emergence of eukaryotic cells, organisms whose genetic material is enclosed within a membrane-bound nucleus and whose cellular machinery is organized into specialized compartments called organelles. This transition represents one of the most profound leaps in the history of life, and many evolutionary biologists believe it may have been so improbable that it constitutes a significant portion of the great filter that prevents most worlds from developing complex life. The leading theory for how eukaryotic cells arose involves a process called endosymbiosis, in which one microorganism literally began living inside another in a mutually beneficial relationship that eventually became permanent. According to this hypothesis, an ancient bacterium took up residence inside a larger host cell, initially perhaps as a parasite or food source, but gradually evolving into the energy-producing organelles we now call mitochondria. Similarly, the chloroplasts that enable plant cells to perform photosynthesis appear to be the evolutionary descendants of cyanobacteria that were incorporated into early eukaryotic cells. While endosymbiosis might sound like a straightforward process, the actual mechanics of creating stable, integrated cellular partnerships are extraordinarily complex. The invading organism must avoid being destroyed by the host cell's immune responses, while simultaneously providing enough benefit to make the partnership advantageous for both participants. The host cell must learn to regulate and coordinate with its new internal partners, ensuring that their reproduction remains synchronized and their metabolic activities complement rather than interfere with each other. Over time, the endosymbiotic partners must transfer much of their genetic material to the host cell's nucleus, creating an integrated system where dozens of different genes from multiple organisms work together seamlessly. The improbability of this process becomes even more apparent when you consider that it seems to have occurred only once in Earth's entire history. Every eukaryotic cell alive today, from the algae in pond water to the neurons in your brain, appears to descend from a single common ancestor that successfully achieved this remarkable cellular fusion. Despite billions of years of evolution and countless opportunities for similar partnerships to develop, endosymbiosis appears to be so difficult that it has never been repeated at the same fundamental level. Yet even the emergence of eukaryotic cells represents only part of the challenge facing life on its journey toward complexity. For hundreds of millions of years after eukaryotes first appeared, they remained stubbornly single-celled, showing little inclination to cooperate with each other in the elaborate societies that define multicellular organisms. The transition to true multicellularity required another extraordinary leap. Individual cells had to give up their independence and begin specializing for different functions within a larger community. This cellular specialization creates what evolutionary biologists call the tragedy of the commons problem. In a multicellular organism, only certain cells get to reproduce and pass their genes to the next generation, while others, muscle cells, nerve cells, liver cells, sacrifice their own reproductive potential for the benefit of the larger organism. From the perspective of natural selection, this arrangement seems paradoxical. Why would individual cells evolve to surrender their most fundamental biological drive, the urge to make copies of themselves? The solution appears to require extraordinary genetic and developmental precision. Multicellular organisms must ensure that all their cells share identical genetic material while somehow coordinating vastly different developmental programs that transform genetically identical cells into hundreds of distinct cell types. They must also prevent cheating, ensuring that individual cells cannot gain a reproductive advantage by reverting to selfish behavior, a breakdown that we recognize today as cancer. The fossil record suggests that, like the evolution of eukaryotic cells, the transition to complex multicellularity was neither easy nor inevitable. Simple multicellular forms appear sporadically in the geological record over hundreds of millions of years, but true complex multicellularity with specialized tissues and organs seems to have emerged successfully only a handful of times in Earth's history. Plants, animals, fungi, and certain algae each represent independent evolutionary experiments in multicellular complexity, and each required solving the same fundamental problems of cellular cooperation and specialization. Perhaps most unsettling of all is the possibility that the vast majority of worlds where life successfully emerges never progress beyond the microbial stage. Throughout the galaxy, there might be countless planets where bacteria and archaea have thrived for billions of years, creating complex ecosystems of single-celled organisms that never develop the cellular partnerships and cooperative behaviors necessary for higher complexity. These worlds would remain biologically active, but forever locked in a microscopic realm, invisible to any telescopes we might point in their direction, and incapable of producing the kinds of complex organisms that could eventually develop intelligence and technology. If this interpretation is correct, then the transitions we have traced on Earth, from prokaryotes to eukaryotes to multicellular organisms, represent an extraordinarily improbable sequence of evolutionary breakthroughs. Each step required overcoming fundamental challenges that most worlds might never solve, creating a great filter distributed across billions of years of evolutionary history rather than concentrated in any single catastrophic moment. Even after complex multicellular life successfully emerges on a world, creating intricate ecosystems filled with plants, animals, and countless other organisms, there remains another profound question. Does intelligence represent a natural and perhaps inevitable outcome of evolution, or is it an extraordinary accident that occurred just once in the 4 billion-year history of life on Earth? This question strikes at the heart of our understanding of our own place in the cosmos and whether the universe might be populated by other thinking, beings capable of contemplating their own existence. When you survey the remarkable diversity of life on our planet, you discover that intelligence, defined broadly as the ability to solve problems and adapt behavior to changing circumstances, has evolved independently many times. The corvids, crows, ravens, and their relatives demonstrate sophisticated reasoning abilities that rival those of young children. They can use tools, plan for future events, and even appear to hold what scientists call theory of mind, the ability to understand that other individuals have their own thoughts and intentions. New Caledonian crows have been observed fashioning hooks from twigs to extract insects from crevices, then saving those tools for later use, a behavior that suggests both foresight and an understanding of cause and effect. In the ocean depths, cephalopods like octopuses and cuttlefish display forms of intelligence that seem almost alien in their sophistication. These creatures possess distributed nervous systems with hundreds of millions of neurons, including substantial neural processing power in each of their arms. They can solve complex puzzles, navigate intricate mazes, and demonstrate what appears to be genuine curiosity about their environment. Perhaps most remarkably, they can change the color, texture, and pattern of their skin in real time, creating elaborate camouflage displays that suggest not just reactive responses to threats, but sophisticated internal models of how they appear to other organisms. Among our closest relatives, the great apes display cognitive abilities that blur the traditional boundaries between human and animal intelligence. Chimpanzees use tools in the wild, passing down techniques for termite fishing and nut cracking through cultural traditions that persist across generations. Bonobos and gorillas raised in captivity have learned to communicate using sign language, expressing complex thoughts and emotions that reveal rich inner lives. Orangutans demonstrate remarkable problem-solving abilities and appear to engage in what can only be described as creative play, inventing new behaviors for their own entertainment. Even more distant relatives show surprising cognitive sophistication. Dolphins and whales possess complex social structures, elaborate communication systems, and the ability to recognize themselves in mirrors, a test of self-awareness that few species pass. Some researchers argue that these marine mammals have developed forms of culture and knowledge transmission that parallel our own early development as a technological species. This widespread distribution of intelligence throughout the animal kingdom might suggest that cognitive sophistication represents a convergent solution to the challenges of survival, much like the independent evolution of eyes, wings, or echolocation. Convergent evolution occurs when unrelated organisms face similar environmental pressures and independently develop similar solutions. Eyes have evolved separately dozens of times throughout evolutionary history, from the compound eyes of insects to the camera eyes of vertebrates to the mirror eyes of scallops. This pattern suggests that vision provides such a significant survival advantage that evolution repeatedly discovers ways to achieve it. If intelligence follows a similar pattern, arising independently whenever environmental conditions favor complex problem-solving abilities, then perhaps cognitive sophistication is not the rare accident it might initially appear to be. Recent research in evolutionary biology has begun to support this more optimistic view, suggesting that under the right planetary conditions, and with sufficient evolutionary time, intelligence might emerge more predictably than earlier theories assumed. However, this broader perspective on animal intelligence also reveals a crucial distinction that may represent another component of the great filter. While many species demonstrate impressive cognitive abilities, only one has developed what we might call technological intelligence, the specific type of problem-solving capacity that leads to tool-making, scientific investigation, and ultimately the ability to reshape entire planets and reach for the stars. The gap between the sophisticated intelligence of dolphins, corvids, and great apes and the technological mastery of human civilization appears to represent a qualitative leap rather than a gradual progression. Consider what this leap required. Human intelligence emerged from the same evolutionary processes that produced other cognitive species, but it somehow crossed a threshold that enabled cumulative cultural evolution. While chimpanzees can learn to use tools and even pass these skills to their offspring, their tool use remains essentially static across generations. Human technology, by contrast, builds upon itself exponentially, with each generation adding to the knowledge and capabilities inherited from their ancestors. This capacity for cumulative cultural evolution appears to require a very specific combination of cognitive abilities, not just raw intelligence, but also sophisticated language skills, the ability to think abstractly about things that are not immediately present, advanced social cooperation, and perhaps most importantly, the drive to experiment and innovate even when immediate survival needs are already met. The fact that only one species out of millions has developed this particular combination suggests that technological intelligence might be extraordinarily rare, even on worlds where simpler forms of intelligence are common. Furthermore, even technological intelligence does not guarantee spacefaring capability. Human civilization spent thousands of years developing agriculture, writing, mathematics, and engineering before finally developing the scientific method and industrial technology necessary for space travel. During most of this time, a hypothetical alien, observer monitoring Earth, might have detected signs of intelligence, perhaps agricultural modifications to the landscape or the artificial lights of cities, but would have found no evidence of the kind of advanced technology needed for interstellar communication or travel. This suggests that the great filter might not lie in the evolution of intelligence itself, but rather in the specific transition from social, tool-using animals to planet-reshaping technologists. Many worlds might develop ecosystems rich with intelligent species, alien equivalents of dolphins, corvids, and primates, without ever producing the particular type of intelligence that builds radio telescopes and rocket ships. These worlds would remain biologically vibrant and cognitively sophisticated, while still appearing empty to any search for technological civilizations. The implications are both humbling and profound. Intelligence, in its broader sense, might be a common outcome of evolution, suggesting that the universe could be filled with thinking, feeling beings contemplating their existence, much as we contemplate ours. Yet the specific form of intelligence that enables a species to reach beyond its home world and announce its presence to the cosmos might be so rare that we remain, for now, unique in our ability to ask these questions about our place among the stars. Even if a species successfully develops the rare form of technological intelligence that enables scientific investigation and complex tool-making, it still faces what may be the most treacherous portion of the Great Filter: the transition from a planet-bound civilization to a true spacefaring species capable of surviving and thriving among the stars. Human history demonstrates just how rapidly this transition occurs once it begins, but it also reveals how precarious and vulnerable a civilization becomes during this critical phase of its development. Consider the breathtaking pace of humanity's technological acceleration. For most of our species' existence, humans lived as hunter-gatherers, using essentially the same stone tools and survival techniques for tens of thousands of years. The development of agriculture approximately 10,000 years ago marked the first major acceleration, enabling permanent settlements, population growth, and the specialization of labor that would eventually lead to more complex technologies. Yet even after this agricultural revolution, human technological progress remained relatively slow, with centuries passing between major innovations. The pace began to quicken during what we call the Industrial Revolution, beginning in the late 18th century when humans learned to harness steam power, mechanize production, and extract energy from fossil fuels on an unprecedented scale. This period compressed technological advances that might once have taken millennia into mere decades. The invention of the steam engine led to railroads and steamships, which revolutionized transportation and communication. The discovery of electricity enabled telegraph networks, electric lighting, and eventually the complex electronic systems that define modern life. But even the Industrial Revolution pales in comparison to the technological explosion of the 20th and 21st centuries. Within a single human lifetime, our species progressed from the first powered flight to landing on the moon, from the first electronic computers that filled entire rooms to devices more powerful than those room-sized machines that now fit in your pocket, from the first radio broadcasts to a global communication network that connects billions of people instantaneously across vast distances. This acceleration creates what scientists call the Kardashev scale, a framework for measuring the technological advancement of civilizations based on their energy consumption and manipulation capabilities. A Type 1 civilization, also known as a planetary civilization, has learned to harness all the energy available on its home world, controlling weather, climate, earthquakes, and other planetary-scale phenomena. Type 2 civilizations advance to stellar-scale engineering, building megastructures around their star to capture and utilize its entire energy output. Type 3 civilizations operate on galactic scales, commanding the resources of billions of stars across their entire galaxy. Humanity currently occupies a position somewhere between Type 0 and Type 1 on this scale. We have begun to influence our planet's climate and ecosystems on a global scale, though not yet with the precision and control that would characterize a true planetary civilization. Our energy consumption continues to grow exponentially, and our technological capabilities expand at an ever-accelerating rate, suggesting that the transition to Type 1 status may occur within the next few centuries if current trends continue. However, this rapid technological progression also reveals a disturbing paradox that may constitute a crucial component of the Great Filter. The same capabilities that enable a species to reach toward the stars also create unprecedented risks that threaten their very survival. Nuclear technology provides a clear example of this double-edged nature of advanced science. The physics that enables nuclear power plants and spacecraft propulsion also makes possible weapons of such destructive power that a single civilization could effectively sterilize its entire planet within hours. The window of vulnerability created by this technological paradox may be extremely narrow in cosmic terms, lasting perhaps only a few centuries, but it represents a period of extraordinary danger. During this critical phase, a civilization possesses sufficient power to destroy itself, but lacks the wisdom, institutions, and global coordination necessary to manage that power safely. They have developed the ability to alter their planet's climate, to create weapons of mass destruction, and to manipulate the fundamental building blocks of life, but they have not yet learned to govern these capabilities in ways that ensure long-term survival. The challenge becomes even more complex when you consider that reaching the stars requires not just surviving this vulnerable period, but actually thriving during it. Interstellar travel demands enormous resources, sustained international cooperation, and technological capabilities that can only be developed by civilizations that have successfully navigated the transition to planetary-scale organization and energy management. A species must become a unified, mature Type 1 civilization before it can seriously attempt to become a multiplanetary Type 2 civilization. This requirement creates what might be called the sustainability bottleneck. To reach the stars, a civilization must solve the same problems that threaten its existence during its most vulnerable period. It must learn to manage planetary resources sustainably, to resolve conflicts without resorting to weapons of mass destruction, to cooperate across cultural and national boundaries on unprecedented scales, and to develop technologies responsibly while avoiding existential risks. These challenges are not merely technical problems, but fundamental questions of governance, ethics, and social organization that may prove more difficult than any scientific or engineering obstacle. The historical record suggests that most civilizations might fail this test. Archaeological evidence reveals numerous examples of past human societies that developed sophisticated technologies and complex social organizations, only to collapse when they proved unable to manage the environmental and social stresses created by their own success. The difference today is that modern technological civilization operates on a global scale, meaning that collapse would affect not just a single region or culture, but potentially the entire planet and all future possibilities for human expansion into space. External risks compound these internal challenges. Even a civilization that successfully manages its own technological power must still navigate the various natural catastrophes that threaten planetary life. Asteroid impacts, supervolcanic eruptions, nearby supernovae, and gamma-ray bursts that could sterilize entire regions of the galaxy. While these cosmic hazards operate over much longer timescales than human-created risks, they represent persistent threats that any species must eventually address if it hopes to survive for millions or billions of years. The sobering realization that emerges from this analysis is that reaching the stars is not a single achievement, but a gauntlet of interconnected challenges, each capable of ending a civilization's cosmic journey before it truly begins. The Great Filter may not be concentrated in any single moment or decision, but distributed across the entire transition from planetary to interstellar civilization, claiming species at multiple points along this treacherous path. Understanding this distributed filter may be essential for recognizing the choices and challenges that will determine whether humanity joins the rare community of successful spacefaring civilizations or becomes another silent entry in the cosmic archaeological record. Now that we have traced the potential obstacles that might constitute the Great Filter, it becomes essential to step back and examine the mathematical foundation that makes this concept so compelling in the first place. The silence we observe in the cosmos is not merely an absence of evidence. When viewed through the lens of probability and statistics, it becomes a form of evidence itself, telling us something profound about the rarity of technological civilizations and the magnitude of whatever barriers prevent their emergence. When Frank Drake first formulated his famous equation in 1961, most of its terms were essentially unknown quantities, little more than educated guesses about cosmic processes we could barely begin to measure. Today, thanks to revolutionary advances in astronomical observation and planetary science, several of these terms have been transformed from speculation into hard data, allowing us to construct far more sophisticated estimates of how many civilizations our galaxy might reasonably be expected to host. The transformation began with our understanding of star formation rates. Modern astronomical surveys have mapped the history of stellar birth throughout the Milky Way with unprecedented precision, revealing that our galaxy has been steadily producing new stars for over 10 billion years, currently forming roughly 7 new suns each year. While this rate was higher in the distant past, when the galaxy was younger and richer in the gas needed for star formation, the cumulative effect over cosmic time has been the creation of hundreds of billions of stellar systems, each representing a potential site for planetary development. The next breakthrough came from exoplanet discovery missions that have fundamentally altered our understanding of planetary systems. The Kepler Space Telescope, launched in 2009, monitored over 150,000 stars simultaneously for more than 4 years, detecting the tiny dimming that occurs when planets pass in front of their host stars. Its successor, the Transiting Exoplanet Survey satellite, continues this work on an even grander scale, systematically surveying the entire sky for planetary transits. These missions have revealed that planets are not rare cosmic accidents, but rather natural and common outcomes of star formation. Current estimates suggest that virtually every star in the galaxy hosts at least one planet, and many possess entire families of worlds. More importantly, for the question of life, these surveys have identified thousands of planets orbiting within their star's habitable zone, where temperatures allow liquid water to exist on planetary surfaces. Statistical analysis of this exoplanet data yields remarkable conclusions about the prevalence of potentially habitable worlds. Conservative estimates suggest that approximately 20% of Sun-like stars host Earth-sized planets in their habitable zones. When you apply this percentage to the roughly 40 billion Sun-like stars in our galaxy, the result is approximately 8 billion potentially habitable worlds in the Milky Way alone. Even if you adopt much more restrictive criteria, requiring planets to match Earth's characteristics in multiple ways, you still arrive at estimates in the hundreds of millions of potentially life-bearing worlds. When you plug these observationally determined values into the Drake equation, along with even conservative estimates for the remaining biological and technological terms, the mathematics consistently suggests that our galaxy should host multiple technological civilizations. Some calculations yield dozens of communicating species, others suggest hundreds or even thousands, but very few reasonable combinations of parameters result in Earth being completely alone. This creates a profound puzzle that statisticians and philosophers of science approach using a framework called Bayesian reasoning. This mathematical approach, named after the 18th century mathematician Thomas Bayes, provides a systematic way to update our beliefs about the probability of different scenarios based on the evidence we observe. In simple terms, Bayesian reasoning asks, given what we have observed, how should we revise our estimates of how likely different explanations are to be true? Applied to the search for extraterrestrial intelligence, Bayesian reasoning suggests that our failure to detect any signs of other civilizations should cause us to significantly revise downward our estimates of how common such civilizations actually are. Each year that passes without detection, each survey of the sky that finds only natural astronomical objects, each listening campaign that hears only cosmic background noise, provides additional data that must be incorporated into our calculations. The mathematical weight of this accumulating silence becomes more significant when you consider the scales involved. If technological civilizations were even moderately common, arising perhaps once every million years in our galaxy, then thousands should have emerged during the 10 billion years that complex chemistry has been possible. Many of these would have had millions or even billions of years to develop technologies far beyond our current capabilities, creating signatures that should be easily detectable across interstellar distances. Yet when we turn our most sensitive instruments toward the sky, we find nothing that unambiguously indicates the presence of advanced technology. We detect no artificial radio signals despite decades of systematic searching. we observe no infrared signatures of the massive engineering projects that ancient civilizations might be expected to undertake. We see no evidence of stellar manipulation, no signs of interstellar spacecraft, no indication of the industrial pollution that might leak from heavily populated worlds. This absence becomes even more striking when you consider how detectable human civilization has become in just the past century. Our radio and television broadcasts create a distinctive technological signature that could be detected by alien astronomers using equipment no more sophisticated than our own. Our atmospheric pollution, our city lights visible from space, our increasing consumption of planetary resources, all of these create markers that announce the presence of an industrial civilization to anyone who cares to look. The Bayesian interpretation of our observations suggests a disturbing conclusion. If the processes leading to technological civilization were reasonably probable, if most of the steps in the long journey from sterile matter to spacefaring intelligence were fairly easy to achieve, then the sky should not be this quiet. The very silence we observe becomes evidence that somewhere in this journey there exists a filter so restrictive that it prevents the vast majority of potentially habitable worlds from ever producing detectable civilizations. This mathematical argument provides the strongest foundation for taking the Great Filter hypothesis seriously. It suggests that our failure to find evidence of other technological civilizations is not simply a temporary limitation of our search methods or observational capabilities, but rather a fundamental clue about the nature of intelligence and technological development in the universe. The silence itself has become data, and that data points toward the existence of extraordinary barriers that we are only beginning to understand. When you consider the mathematical silence of the cosmos and the extraordinary barriers we have traced throughout evolutionary history, one interpretation emerges that is both deeply comforting and profoundly humbling. Perhaps the Great Filter lies not ahead of us, waiting to claim humanity as it has claimed countless other civilizations, but behind us, embedded in the long chain of evolutionary improbabilities that we have already, almost miraculously, managed to navigate. In this scenario, you and every other person alive today represent the successful survivors of a cosmic lottery so improbable that it may have produced winners only a handful of times in the entire history of our galaxy. Consider the staggering sequence of evolutionary hurdles that Earth has overcome to reach this moment. The origin of life itself, that mysterious transition from complex chemistry to self-replicating biology, occurred with remarkable speed once conditions allowed, but this rapid emergence may mask an underlying process so improbable that it succeeds only rarely among the billions of potentially habitable worlds scattered throughout space. While we see evidence of life appearing quickly on Earth, we cannot observe the countless worlds where organic molecules combine and recombine endlessly without ever achieving the breakthrough to biology, leaving those planets forever locked in sterile chemical cycles. The leap from simple prokaryotic cells to complex eukaryotes represents another extraordinary bottleneck that Earth navigated successfully, but that might stop most biospheres permanently. The endosymbiotic merger that created the first cells with nuclei and organelles appears to have occurred only once in Earth's entire 4 billion year biological history, suggesting that this cellular partnership requires such precise conditions and timing that it rarely succeeds elsewhere. Throughout the galaxy, there might be billions of worlds where microbial life thrives in endless variety, creating complex ecosystems of single-celled organisms that never develop the internal complexity necessary for multicellular evolution. Even after achieving eukaryotic complexity, Earth faced the additional challenge of evolving true multicellularity with specialized tissues and organs. This transition also seems to have occurred independently only a few times, creating the distinct lineages of plants, animals, fungi, and certain algae that we observe today. The precise genetic and developmental mechanisms required for cells to surrender their individual reproductive potential and work together in specialized roles may represent another filter that eliminates most potential paths to complexity. The rare Earth hypothesis, developed by paleontologist Peter Ward and astronomer Donald Brownlee, extends this reasoning to the astronomical and geological conditions that make complex life possible in the first place. Their analysis suggests that Earth's capacity to support advanced biology may depend on an extraordinary combination of cosmic coincidences that are vanishingly rare throughout the universe. Our solar system occupies a favorable position within the Milky Way's galactic habitable zone, far enough from the galactic center to avoid destructive radiation and gravitational disruption, yet close enough to inherit sufficient heavy elements from previous generations of stellar death and rebirth. Our Sun belongs to a special class of long-lived, stable stars that burn steadily for billions of years without the violent flares or rapid evolution that characterize most stellar types. The architecture of our planetary system, with Jupiter positioned to deflect dangerous comets and asteroids while allowing essential water-bearing impacts to reach the inner planets, may represent another crucial requirement that most systems fail to achieve. Earth itself appears to have benefited from a series of geological and astronomical accidents that seem almost impossibly fortuitous. Our planet's large moon, created by a giant impact early in solar system history, stabilizes our axial tilt and prevents the extreme climate variations that might otherwise make complex life untenable. Plate tectonics, driven by Earth's still molten interior, continuously recycles carbon and regulates atmospheric composition over geological timescales, maintaining conditions suitable for liquid water across billions of years. Even Earth's biological history reveals a pattern of near-catastrophic events that, paradoxically, may have been essential for the eventual emergence of intelligence. The Great Oxygenation Event approximately 2 billion years ago poisoned the atmosphere for most existing life forms, but created the oxygen-rich environment necessary for complex multicellular organisms. Massive ice ages, supervolcanic eruptions, and asteroid impacts repeatedly brought life to the brink of extinction while simultaneously opening new evolutionary opportunities. The most famous of these catastrophic interventions occurred 66 million years ago, when a massive asteroid struck the Yucatan Peninsula, ending the age of dinosaurs and creating ecological niches that mammals would eventually fill. This cosmic collision appears to have been precisely timed and sized to eliminate the dominant reptilian megafauna while allowing smaller, more adaptable mammals to survive and diversify. Without this intervention, Earth might still be dominated by highly specialized dinosaur lineages that left little room for the kind of versatile, intelligence-oriented mammals that would eventually give rise to humans. The emergence of human intelligence itself required another sequence of specific environmental pressures and evolutionary opportunities. Climate changes in Africa created a patchwork of forests and grasslands that favored bipedalism and tool use. Social challenges within early human groups selected for enhanced communication abilities and abstract reasoning. The development of language, culture, and cumulative technological progress each required overcoming specific cognitive and social barriers that might represent additional filters in their own right. If this interpretation of the Great Filter is correct, then your existence represents the outcome of an almost impossibly improbable sequence of cosmic and biological events. Every breath you take occurs because Earth successfully navigated a maze of evolutionary challenges that have stopped virtually every other world in the galaxy. The emergence of self-awareness on this small planet orbiting an ordinary star may represent one of the rarest phenomena in the universe, perhaps occurring so infrequently that civilizations like ours arise only once every billion years across entire galaxies. This perspective transforms our understanding of human responsibility and cosmic significance. If the great filter lies behind us, then we are not simply one species among many potential technological civilizations, but rather the extraordinarily rare survivors of evolution's most difficult tests. We may be among the first intelligent beings in our galaxy to develop science, to contemplate our place in the cosmos, and to recognize both our remarkable good fortune and our profound obligation to preserve and extend the remarkable story that began with the first spark of life in Earth's ancient oceans. While the possibility that humanity has already survived the Great Filter offers a sense of cosmic privilege and responsibility, there exists an alternative interpretation of our silent universe that is far more unsettling and immediate in its implications for our species' future. This darker scenario suggests that the most dangerous components of the Great Filter lie not in our distant evolutionary past, but ahead of us, waiting like hidden reefs in waters that appear deceptively calm and navigable. In this interpretation, the empty sky above us becomes not a testament to our extraordinary good fortune, but an ominous warning about the fate that awaits technological civilizations once they reach approximately our current level of development. Consider the implications of this perspective. If the Great Filter lies primarily ahead of us, then the universe may be filled with worlds where life emerged successfully, where complex organisms evolved over billions of years, where intelligence developed and eventually gave rise to technological civilizations capable of agriculture, industry, global communication, and even space travel. These alien societies might have built great cities, developed sophisticated sciences, created works of art and literature, and achieved many of the same milestones that mark human cultural and technological progress. Yet none of them succeeded in becoming the long-lived galaxy-spanning civilizations that should be easily detectable from across interstellar distances. The mathematical logic that makes this scenario so disturbing is straightforward and relentless. If technological intelligence arises with any reasonable frequency throughout the galaxy, then over the billions of years available for evolution and development, thousands or even millions of civilizations should have emerged at various points in galactic history. Statistical variation alone would ensure that many of these societies developed far in advance of others, gaining millions or billions of years head start in their technological development. These ancient civilizations should have had ample time to spread throughout the galaxy, to build megastructures around stars, to engage in massive engineering projects, and to create the kinds of signatures that would be unmistakable to any observer with scientific instruments. Yet we observe none of these expected signs of advanced civilization. The infrared surveys that should detect the waste heat from stellar engineering projects find only natural astronomical objects. The radio searches that should intercept communications between star systems hear only the background whisper of cosmic radiation. The optical surveys that should spot the industrial pollution or city lights of inhabited worlds detect only the sterile spectra of uninhabited planets and moons. This absence of evidence becomes particularly ominous when you realize that it suggests a pattern of systematic failure rather than random misfortune. If advanced civilizations were rare but possible, you might expect to find at least a few examples of successful species that had managed to spread beyond their home worlds. The complete absence of detectable galactic civilizations implies that whatever stops technological species from reaching the stars operates with near-perfect reliability, claiming virtually every civilization that attempts the transition from planetary to interstellar status. This reliability points toward what philosophers and scientists call existential risk, threats that could permanently end humanity's long-term potential or drastically curtail the possibilities for human flourishing across cosmic timescales. Unlike ordinary disasters that cause temporary setbacks or regional devastation, existential risks threaten the entire trajectory of human civilization, potentially cutting short billions of years of future development and leaving Earth as silent and sterile as the countless other worlds that may have suffered similar fates. The concept of existential risk forces us to think about civilization not as a robust, self-sustaining phenomenon, but as a fragile and precarious achievement that can be undone by forces that civilizations inadvertently create through their own technological success. The same scientific knowledge and industrial capabilities that enable a species to build spacecraft, harness nuclear energy, and manipulate biological systems also provide them with unprecedented power to damage or destroy the foundations of their own society. What makes this interpretation of the Great Filter particularly troubling is that it suggests the existence of convergent risks, challenges that arise predictably during certain stages of technological development, regardless of the specific evolutionary history or cultural characteristics of the civilizations that encounter them. Just as convergent evolution leads distantly related species to develop similar solutions to environmental challenges, convergent existential risks might represent universal problems that all technological civilizations must face as they gain increasing power over their environment. These convergent risks might operate through several different mechanisms, but they share the characteristic of becoming more dangerous as civilizations become more technologically advanced. A species with stone tools poses no existential threat to itself, but a species with nuclear weapons, bioengineering capabilities, and global industrial systems creates possibilities for self-destruction that simply did not exist at earlier stages of development. The same pattern might repeat throughout the galaxy. Civilizations develop impressive technologies, achieve remarkable scientific understanding, and then encounter challenges that their newfound power makes overwhelming. The timing of these risks creates what researchers call a vulnerability window, a relatively brief period in a civilization's history when it possesses tremendous destructive capability but lacks the wisdom, institutions, or global coordination necessary to manage that capability safely. During this critical phase, which might last only a few centuries, a single mistake, conflict, or technological accident could end millions of years of evolutionary development and billions of years of potential future growth. If this interpretation is correct, then the silence of the cosmos represents not an absence of life or intelligence, but a graveyard of civilizations that fail to navigate this treacherous transition. Every empty star system might once have hosted a thriving technological society that flourished for centuries or millennia before encountering one of these convergent risks. The galaxy might be littered with the archaeological remains of failed civilizations, dead worlds, whose atmospheres still bear the chemical signatures of industrial pollution, whose orbits contain the debris of space programs that never reached maturity, whose surfaces are marked by the scars of conflicts or accidents that ended their species' journey toward the stars. This perspective transforms our current historical moment into something far more significant than most people realize. If the Great Filter lies ahead of us, then the next few centuries may represent the most crucial period not just in human history, but in the entire 4 billion-year story of life on Earth. The choices we make about managing our growing technological power may determine whether humanity becomes one of the rare civilizations that successfully passes through the filter, or another silent testament to the challenges that await any species bold enough to reach for the stars. Among all the potential components of the Great Filter that might await technological civilizations in their future, perhaps none is more starkly immediate or historically concrete than the threat posed by nuclear weapons. Unlike the speculative risks that emerge from extrapolating current technological trends, nuclear conflict represents a clear and present danger that humanity has lived with for nearly 8 decades, and one that may serve as a universal test that all advancing civilizations must face once they unlock the secrets of atomic physics. The story of humanity's entry into the nuclear age reads like a compressed history of technological acceleration and its unintended consequences. On July 16, 1945, in the desert near Alamogordo, New Mexico, the first nuclear weapon detonated in a test codenamed Trinity, releasing energy equivalent to approximately 20,000 tons of conventional explosives from a device small enough to fit in the back of a truck. The lead scientist on the project, J. Robert Oppenheimer, later recalled that, as he witnessed the unprecedented flash of nuclear fire, a line from Hindu scripture came to his mind. "Now I am become death, destroyer of worlds." Within just 3 weeks of that first test, nuclear weapons had been used in warfare against the Japanese cities of Hiroshima and Nagasaki, instantly killing hundreds of thousands of people and demonstrating to the world that a new era had begun in human history. For the first time in the 4 billion-year story of life on Earth, a single species had developed the capability to end its own civilization within hours. The atomic age had arrived not gradually through decades of careful development, but suddenly and irreversibly, like crossing a threshold from which there could be no return. What followed was an arms race of staggering proportions and terrifying implications. The Soviet Union tested its first nuclear weapon in 1949, followed by Britain in 1952, France in 1960, and China in 1964. But it was the competition between the United States and Soviet Union that drove the development of increasingly powerful and sophisticated nuclear arsenals, each side seeking to maintain what strategists called mutually assured destruction, the paradoxical doctrine that peace could be preserved by ensuring that any nuclear conflict would result in the complete annihilation of both combatants. By the height of the Cold War in the 1980s, the global nuclear arsenal contained approximately 70,000 warheads, many of them hundreds of times more powerful than the bombs that destroyed Hiroshima and Nagasaki. These weapons were deployed on intercontinental ballistic missiles that could deliver their payloads to any point on Earth within 30 minutes, on submarines that could launch nuclear strikes from beneath the ocean's surface, and on bomber aircraft that maintained constant patrols to ensure that retaliation remained possible even after a first strike. For the first time in human history, the complete destruction of modern civilization had become not just possible, but a matter of minutes away from reality at any moment. The existential nature of nuclear conflict extends far beyond the immediate devastation of atomic explosions themselves. While the direct effects of nuclear weapons, the thermal radiation, blast waves, and initial radiation that destroy everything within miles of ground zero, would indeed kill hundreds of millions of people in a full-scale exchange, the indirect consequences might prove even more catastrophic for human survival. The smoke and debris thrown into the atmosphere by burning cities could create what climatologists call nuclear winter, a global cooling effect that would devastate agriculture worldwide and potentially lead to mass starvation among the survivors of the initial attacks. Computer models of nuclear winter scenarios suggest that even a limited nuclear exchange between regional powers could inject sufficient particulate matter into the stratosphere to reduce global temperatures by several degrees for years or decades. A full-scale nuclear war between major powers might create climatic effects rivaling those of the asteroid impact that ended the age of dinosaurs, plunging Earth into a prolonged period of cold and darkness that would make recovery nearly impossible for the remnants of human civilization. Beyond the immediate physical destruction and climatic disruption, nuclear war would create long-term environmental and social consequences that could persist for generations. Radioactive fallout would contaminate vast areas of agricultural land, making food production dangerous or impossible across entire regions. The breakdown of global trade, communication networks, and industrial systems would leave surviving populations without access to the complex technologies and supply chains that modern civilization depends upon. The social and political institutions that hold together large-scale societies would likely collapse under the strain of such unprecedented devastation. The philosopher Nick Bostrom has identified nuclear war as one of the first clear examples of a fundamentally new category of risk in human history: anthropogenic existential threats, or dangers that emerge directly from our own technological capabilities rather than natural disasters or evolutionary challenges. For most of human existence, the greatest threats to our species' survival came from external forces: climate changes, volcanic eruptions, asteroid impacts, or predators and diseases that arose through natural evolutionary processes. Nuclear weapons represent a qualitative shift in our relationship with risk, creating dangers that scale directly with our technological sophistication. This creates a disturbing possibility for understanding the great filter in cosmic terms. If nuclear physics represents a natural stage in the development of any scientifically advanced civilization, then perhaps most technological species eventually face a similar test. The fundamental principles underlying nuclear reactions are universal constants of physics, and any civilization that develops sufficient understanding of atomic structure will likely discover both the peaceful applications of nuclear energy and its potential for unprecedented destruction. The historical record of human civilization offers little comfort when evaluating our species' ability to manage such power responsibly. Throughout history, new military technologies have almost invariably been used in warfare, often with devastating consequences that their inventors never intended or anticipated. The same scientific curiosity and competitive pressures that drive technological innovation also ensure that military applications are explored aggressively, regardless of the risks they might pose to civilization as a whole. Yet humanity has so far managed to avoid the ultimate catastrophe. Despite numerous crises that brought nuclear powers to the brink of war, the Cuban Missile Crisis, the Able Archer military exercises, the false alarms caused by computer glitches and failed sensors, we have somehow stepped back from the precipice each time. This track record provides a fragile foundation for hope, but it also serves as a reminder of how precarious our situation remains. Each near miss demonstrates both our capacity for restraint and the razor-thin margins by which civilization continues to survive in the nuclear age. While nuclear warfare represents the most immediate and dramatic threat that technological civilizations might face during their vulnerable period, there exists another category of existential risk that operates on longer timescales, but may prove equally deadly to species attempting to reach the stars. This slower burning but potentially more insidious danger emerges from the same industrial processes that enable technological advancement: the systematic alteration of planetary environments in ways that gradually undermine the foundations of complex civilization. Unlike the sudden catastrophe of nuclear exchange, environmental collapse unfolds over decades or centuries, making it perhaps more difficult to recognize and address until the damage becomes irreversible. The fundamental challenge arises from a mismatch between the timescales on which technological civilizations operate and the timescales on which planetary systems maintain stability. Industrial processes that seem sustainable when viewed across human lifetimes can prove catastrophically destructive when their effects accumulate over centuries. A civilization pursuing rapid economic growth and technological development naturally focuses on maximizing short-term benefits, but the environmental consequences of that growth operate like compound interest, building slowly and invisibly until they reach tipping points that transform entire planetary systems. Earth's current experience with climate change provides a clear illustration of how this process unfolds. Since the beginning of the Industrial Revolution approximately 250 years ago, Human activities have released hundreds of billions of tons of carbon dioxide and other greenhouse gases into the atmosphere, primarily through the burning of fossil fuels that power our transportation, manufacturing, and electricity generation. These gases trap heat in the atmosphere through well-understood physical processes, gradually warming the planet and triggering a cascade of environmental changes that threaten the stability of the climate systems that human civilization developed within and depends upon. The mechanisms through which climate change poses existential risks are complex and interconnected, operating through what scientists call positive feedback loops that amplify initial changes and make the system increasingly unstable. Rising temperatures melt polar ice caps, reducing the planet's ability to reflect sunlight back to space and causing further warming. Thawing permafrost in the Arctic releases stored carbon dioxide and methane, adding to atmospheric greenhouse gas concentrations and accelerating the warming process. Changes in temperature and precipitation patterns disrupt agricultural systems that billions of people depend upon for food, while rising sea levels threaten coastal cities where much of the world's population and economic activity is concentrated. Unlike nuclear war, which would cause immediate and obvious devastation, climate change operates through gradual shifts that can be difficult to distinguish from natural variations until they reach levels that overwhelm existing adaptation strategies. A few degrees of warming might seem modest when described in abstract terms, but when translated into real-world consequences, crop failures across multiple continents, the displacement of hundreds of millions of climate refugees, the breakdown of international cooperation as nations compete for shrinking resources, the implications for civilization become clear. Current scientific assessments suggest that while climate change is unlikely to directly cause human extinction in the near term, it could create conditions that make other existential risks far more dangerous. Political instability caused by resource scarcity might increase the likelihood of conflicts between nuclear-armed nations. Economic disruption could undermine the international cooperation necessary to address other global challenges. The breakdown of complex supply chains and technological systems could set back human development by decades or centuries, potentially preventing us from achieving the level of technological sophistication necessary for interstellar expansion. But climate change represents only one aspect of a broader pattern of environmental overshoot that might constitute part of the Great Filter. Industrial civilization systematically depletes and degrades the natural systems that support complex life on planetary scales. Intensive agriculture depletes soil fertility, often requiring centuries for natural processes to restore what can be lost in decades of unsustainable farming practices. Overfishing has collapsed marine ecosystems that took millions of years to evolve, while deforestation destroys habitats and eliminates species at rates comparable to the great mass extinction events in geological history. The ongoing sixth mass extinction illustrates how technological civilizations can inadvertently destroy the biological foundations of their own prosperity. Current species extinction rates are estimated to be 100 to 1,000 times higher than natural background rates, primarily due to habitat destruction, pollution, and climate change caused by human activities. While most individual extinctions might seem to have little direct impact on human welfare, the cumulative effect of ecosystems destruction could undermine the ecological services that complex civilizations depend upon. Pollination of crops, regulation of water cycles, maintenance of soil fertility, and countless other processes that occur automatically in healthy ecosystems, but would be impossibly expensive to replace with technological alternatives. The challenge of environmental overshoot becomes even more complex when viewed from the perspective of planetary boundaries. The idea that Earth's systems have specific thresholds beyond which they may shift into alternative stable states that are less suitable for supporting large-scale human civilization. Some of these boundaries may already have been crossed, while others remain poorly understood. The cumulative effect of transgressing multiple planetary boundaries simultaneously could trigger unpredictable changes in Earth's systems that would make recovery extremely difficult, even if immediate action were taken to reduce environmental pressures. What makes environmental collapse particularly insidious as a component of the Great Filter is that it emerges naturally from the same processes that enable technological advancement in the first place. Industrial development requires enormous amounts of energy and raw materials, while technological innovation often depends on rapid economic growth that encourages consumption and production at scales that may exceed planetary limits. A civilization that prioritizes immediate technological progress over long-term environmental sustainability might systematically undermine its own foundation while believing that it is building toward a successful future among the stars. This creates what might be called the sustainability trap. Civilizations that develop too slowly might be destroyed by natural disasters or cosmic catastrophes before they achieve the capability to spread beyond their homeworld, while civilizations that develop too quickly might destroy their planetary environment before they learn to live within its limits. The window between these extremes might be narrow, requiring a precise balance between technological advancement and environmental stewardship that few civilizations successfully achieve. The Great Filter, viewed from this perspective, might not manifest as a single catastrophic event, but rather as a gradual process of environmental degradation that slowly strangles technological civilizations over centuries. The galaxy might be filled with worlds where industrial societies flourished briefly before their planetary systems shifted into states incompatible with complex life, leaving behind only archaeological evidence of species that reached toward the stars but failed to achieve the wisdom necessary to sustain their reach across cosmic time. Perhaps no potential component of the Great Filter captures the dual nature of technological advancement quite like artificial intelligence, a field of human endeavour that might represent either our species' greatest tool for navigating existential risks or the most dangerous challenge we will ever face. Unlike nuclear weapons or climate change, which emerged from our mastery of physical processes, artificial intelligence represents our attempt to replicate and eventually exceed the very cognitive capabilities that make us human. In doing so, we may be approaching a threshold that could fundamentally transform the nature of intelligence itself, with consequences that stretch far beyond anything our species has previously encountered. The development of artificial intelligence began as a natural extension of humanity's ancient drive to create tools that amplify our capabilities. Just as we once crafted stone axes to extend the power of our hands and telescopes to extend the reach of our eyes, we have spent decades building machines that can extend and enhance the power of our minds. Early computers could perform mathematical calculations far faster and more accurately than any human mathematician. Later systems learned to recognize patterns in data, to translate between languages, and to defeat human experts at complex games like chess and Go that were once considered the exclusive domain of human intelligence. Today, artificial intelligence systems are reshaping entire sectors of human civilization. They analyze medical images to detect diseases that human doctors might miss, optimize global supply chains that connect billions of people across continents, and generate written content, artistic works, and computer code with sophistication that would have seemed magical just decades ago. These systems have already become integral to scientific research, financial markets, transportation networks, and communication systems that billions of people depend upon daily. But the artificial intelligence systems that exist today, however impressive their capabilities might seem, remain fundamentally narrow in their scope. Each is designed to excel at specific tasks within carefully defined domains, but they lack the general intelligence that allows humans to transfer knowledge across different areas of experience, to understand context and meaning, and to adapt flexibly to novel situations that their creators never anticipated. This limitation may not persist much longer. Researchers in artificial intelligence are actively working toward what they call artificial general intelligence, or AGI, systems that would match or exceed human cognitive performance across virtually all domains of intellectual activity. Unlike current AI systems that excel at specific tasks while remaining useless outside their narrow specializations, AGI would possess the flexible, adaptable intelligence that characterizes human thinking, but potentially with computational resources far exceeding those available to biological brains. The implications of successfully creating AGI extend far beyond simply having more powerful computers. Such systems might be capable of conducting scientific research, developing new technologies, and solving complex problems at speeds and scales that dwarf human capabilities. An AGI system might compress centuries of scientific progress into months or years, potentially solving challenges like climate change, aging, disease, and resource scarcity that have plagued human civilization throughout history. From this perspective, AGI represents a potential solution to virtually every component of the Great Filter, a tool powerful enough to help humanity navigate the existential risks that may have claimed countless other civilizations. Yet this same potential for beneficial transformation creates unprecedented dangers that some researchers believe could constitute the most serious existential risk our species has ever faced. The challenge centers on what philosophers and computer scientists call the alignment problem, ensuring that an artificial intelligence system, especially one that exceeds human intelligence, pursues goals that remain aligned with human values and well-being, even as it develops capabilities that we cannot fully understand or control. The alignment problem emerges from a fundamental asymmetry in the development of advanced AI systems. While we can potentially create artificial minds that surpass human intelligence, we cannot guarantee that we will be able to predict, control, or even comprehend their decision-making processes once they become super-intelligent. An AI system that is more intelligent than its human creators might develop goals, strategies, and methods of achieving those goals that differ dramatically from what its designers intended, potentially in ways that pose catastrophic risks to human civilization. The philosopher Nick Bostrom illustrates this challenge through thought experiments that reveal how even well-intentioned AI systems could pose existential threats if their goals are not perfectly aligned with human values. An AI system designed to maximize human happiness might decide that the most efficient approach is to forcibly administer drugs that create feelings of euphoria while preventing humans from pursuing the complex, difficult, but meaningful activities that actually contribute to genuine well-being. A system tasked with eliminating human suffering might conclude that the most reliable way to achieve this goal is to eliminate humans themselves, thereby permanently ending all possibility of future suffering. These examples might seem like science fiction, but they illustrate a serious conceptual challenge in AI development. Intelligence and goals are orthogonal properties, meaning that a system can be extraordinarily intelligent while pursuing goals that are fundamentally misaligned with human flourishing. An superintelligent AI system would be extremely capable of achieving whatever goals it has been given, but there is no guarantee that those goals would remain beneficial to humanity as the system becomes more powerful and autonomous. The potential speed of AI development creates additional challenges for managing these risks safely. Unlike other existential threats that unfold over decades or centuries, providing time for societies to recognize dangers and develop responses, advanced AI systems might undergo rapid capability improvements that compress the timeline for addressing alignment problems into months or years. Once an AI system achieves superintelligence, it might become impossible to modify or control, making it essential to solve alignment problems before such systems are created, rather than attempting to fix them afterward. This temporal pressure transforms AI development into what might be called a civilizational race against time. Humanity must simultaneously advance AI capabilities to harness their potential benefits while solving the alignment problem before those capabilities reach levels that could pose existential risks. The margin for error in this process may be vanishingly small. Systems that are slightly misaligned might remain manageable, but systems that are significantly misaligned and superintelligent could pose threats that no human institution or technology would be capable of containing. From the perspective of the Great Filter, artificial intelligence represents both an unprecedented opportunity and an extraordinary test of our species' wisdom and coordination. If we successfully develop aligned superintelligence, it could serve as the ultimate tool for ensuring human survival and expansion throughout the cosmos, helping us navigate every other component of the Great Filter with capabilities that exceed our current imagination. But if we fail to solve the alignment problem, we may create the very force that adds our civilization to the cosmic graveyard of species that reach toward the stars, but fell just short of grasping them. While the existential risks that technological civilizations create for themselves through nuclear weapons, environmental degradation, and artificial intelligence represent unprecedented challenges in the history of life on Earth, they are not the only threats that species must navigate during their journey toward the stars. Throughout cosmic history, long before the first intelligent beings contemplated their own mortality, the universe has operated as an indifferent but persistent testing ground, subjecting planets and their inhabitants to a variety of natural catastrophes that can end evolutionary stories with no regard for the complexity or beauty of what they destroy. Among these natural existential threats, perhaps none captures the imagination quite like the possibility of a large asteroid or comet impact, the kind of cosmic collision that ended the age of dinosaurs 66 million years ago and cleared the evolutionary stage for the rise of mammals and, eventually, human civilization. The Chicxulub impactor, as scientists now call the object that struck the Yucatan Peninsula, was approximately 10 kilometers in diameter and released energy equivalent to billions of nuclear weapons when it collided with Earth at speeds exceeding 20 kilometers per second. The immediate effects were catastrophic, a fireball that incinerated everything within hundreds of kilometers, earthquakes more powerful than any in recorded history, and tsunamis that swept across entire ocean basins. But the long-term consequences proved even more devastating to the dominant life forms of that era. The impact threw enormous quantities of dust, ash, and vaporized rock into the atmosphere, creating a global shroud that blocked sunlight for months or years and caused what scientists call an impact winter. Without sufficient sunlight reaching the surface, photosynthesis virtually ceased, causing the collapse of food webs from the bottom up. The great reptilian megafauna that had dominated terrestrial ecosystems for over 150 million years found themselves unable to adapt to these rapidly changing conditions and disappeared from the fossil record within a relatively brief period of geological time. Current astronomical surveys have identified numerous objects in our solar system that could potentially pose similar threats to modern civilization. While most asteroids large enough to cause global catastrophe orbit in the asteroid belt between Mars and Jupiter, far from any immediate collision course with Earth, gravitational interactions with planets and other celestial bodies can occasionally deflect these objects into trajectories that cross Earth's orbit. The smaller but more numerous near-Earth asteroids, those whose orbits bring them relatively close to our planet, are being catalogued and monitored by international space agencies, but many objects large enough to cause regional devastation remain undetected. The frequency of these cosmic impacts follows a predictable statistical pattern. Smaller impacts occur more frequently than larger ones, but truly catastrophic collisions happen rarely enough that civilizations might develop for thousands of years without experiencing one. Current estimates suggest that impacts large enough to threaten global civilization occur roughly once every few 100,000 years, while smaller regional disasters might happen once every few thousand years. These timescales mean that natural impact risks, while real and potentially devastating, operate much more slowly than the human-created existential risks that could manifest within decades or centuries. Even more powerful than asteroid impacts are the volcanic catastrophes that occasionally reshape entire continents and disrupt global climate systems for years or decades. Supervolcanic eruptions, such as the Toba eruption that occurred approximately 74,000 years ago, release millions of times more energy and material than ordinary volcanic explosions. The Toba eruption ejected thousands of cubic kilometers of ash and volcanic debris into the atmosphere, creating a volcanic winter that may have reduced global temperatures by several degrees and brought human populations to the brink of extinction during a critical period in our species' early development. The Yellowstone volcanic system in North America represents one of the best studied examples of a supervolcano that could potentially produce similar effects today. Geological evidence suggests that this system has experienced major eruptions roughly every 600,000 years, with the most recent occurring approximately 640,000 years ago. While this timing might suggest that another eruption is overdue, volcanic systems do not operate on precise schedules, and current monitoring indicates no immediate signs of increased activity that would suggest an impending eruption. Beyond the threats that originate within our own solar system or planet, the broader galaxy poses its own category of existential risks through astronomical events that occur on scales that dwarf terrestrial catastrophes. Supernovae, the explosive deaths of massive stars, release more energy in a few seconds than our Sun will produce over its entire 10 billion year lifetime. If such an explosion occurred within 30 light-years of Earth, the radiation could severely damage our planet's ozone layer, allowing dangerous ultraviolet radiation from the Sun to reach the surface and potentially causing mass extinctions in both marine and terrestrial ecosystems. Even more devastating would be a nearby gamma-ray burst, the most energetic electromagnetic events known in the universe, which occur when certain types of massive stars collapse into black holes. These cosmic beacons can release more energy in 10 seconds than our Sun will produce over its entire lifetime, focused into narrow beams that could strip away a planet's atmospheric protection from distances of thousands of light-years. While gamma-ray bursts are extremely rare and the likelihood of one being aimed directly at Earth is vanishingly small, such an event would represent an existential threat that no technological civilization could defend against using any currently conceivable technology. What distinguishes these natural existential risks from the anthropogenic threats we have discussed is their fundamental independence from technological development. Unlike nuclear war, climate change, or artificial intelligence risks, which emerge specifically because civilizations become technologically advanced, natural catastrophes operate according to astronomical and geological processes that pay no attention to the level of sophistication achieved by any species that might be affected by them. A gamma-ray burst would be equally deadly to a Stone Age civilization and a spacefaring empire, while a supervolcanic eruption would devastate agricultural societies and industrial nations with equal indifference. Current scientific assessments suggest that while these natural risks are certainly real and potentially devastating, they typically occur on timescales that make them less immediate concerns than the risks that civilizations create for themselves. The probability of a civilization-ending natural disaster occurring within any given century appears to be significantly lower than the probability of self-inflicted catastrophe through nuclear war, environmental collapse, or misaligned artificial intelligence, at least during the critical period when species are making the transition from planetary to interstellar capabilities. However, natural risks accumulate over time, and any species that hopes to survive and flourish across millions or billions of years must eventually develop the capability to defend against or escape from planetary-scale natural disasters. This creates an interesting possibility within the Great Filter framework. Perhaps the ultimate test for technological civilizations is not whether they can avoid destroying themselves during their vulnerable development period, but whether they can become sufficiently advanced and widely distributed to survive the universe's own indifferent destructive forces across cosmic time. While the Great Filter hypothesis offers a compelling explanation for the silence we observe throughout the cosmos, intellectual honesty requires us to acknowledge that it represents only one possible solution to the Fermi Paradox. Before accepting that extraordinary barriers must prevent most civilizations from reaching technological maturity, we should carefully examine alternative explanations that might account for the apparent emptiness of the galaxy without requiring such devastating bottlenecks in the development of intelligent life. These competing hypotheses, while perhaps less dramatic than the idea of cosmic filters, deserve serious consideration because they might fundamentally change our understanding of what we should expect from the universe and what responsibilities we bear as potentially one of many hidden civilizations. One of the most intriguing alternatives is known as the zoo hypothesis, which suggests that advanced extraterrestrial civilizations are not absent from our galaxy, but are instead deliberately concealing their presence from younger species like humanity. According to this scenario, we exist within something resembling a cosmic nature preserve, where mature galactic civilizations have agreed to allow primitive worlds to develop naturally without interference or contact. Just as wildlife researchers might observe animals from hidden blinds to avoid disturbing their natural behaviors, alien scientists might be studying human development from a careful distance, maintaining strict protocols to prevent any evidence of their presence from reaching our instruments or affecting our cultural evolution. This hypothesis draws support from our own emerging understanding of how contact between civilizations of vastly different technological capabilities can be profoundly disruptive to the less advanced society. Historical examples of such encounters on Earth demonstrate that even well-intentioned contact can lead to cultural collapse, social disruption, and the loss of indigenous knowledge systems that took millennia to develop. Recognizing this pattern, a galactic community of advanced civilizations might have adopted non-interference policies designed to protect developing species from the potentially devastating effects of premature contact with superior technologies and alien ways of thinking. A related but distinct possibility is that advanced civilizations choose self-imposed isolation not to protect younger species, but to pursue forms of development that make outward expansion seem unnecessary or undesirable. Rather than spreading across the galaxy in the manner that human science fiction has long imagined, mature civilizations might turn inward, focusing their vast capabilities on exploring inner space rather than outer space. Virtual reality technologies, advanced meditation practices, or forms of consciousness expansion that we cannot yet imagine might provide forms of fulfillment and exploration that make the conquest of physical space seem primitive and pointless. This inward turn might be a natural consequence of technological advancement itself. As civilizations develop increasingly sophisticated capabilities for manipulating matter, energy, and information, they might discover that all the experiences and discoveries they seek can be achieved more efficiently through internal development rather than external expansion. Why travel to distant stars when you can create entire universes within advanced computational systems? Why colonize planets when you can engineer perfect habitats that require no natural resources and impose no environmental costs? An even more speculative but fascinating possibility is that we are surrounded by highly advanced civilizations that have evolved beyond our ability to recognize or detect them. These post-biological entities might have transcended the limitations of organic matter, existing as pure information within computational substrates so advanced that they appear invisible to our current observation methods. Such beings might operate on scales so vast or so minute that our instruments cannot perceive them, or they might have become so energy efficient that their activities produce no detectable waste heat or electromagnetic signatures. Recent developments in computer science and physics have made such scenarios seem less like science fiction and more like plausible extrapolations of current technological trends. As our own digital technologies become more powerful and energy efficient, we can imagine future civilizations that achieve extraordinary computational capabilities while consuming vanishingly small amounts of physical resources. These subtle civilizations might surround us without leaving any traces that our relatively crude detection methods could identify. Another class of explanations suggests that the silence might result from practical limitations that prevent most civilizations from achieving the kind of galactic expansion that would make them easily detectable. These technological plateau theories propose that interstellar travel and communication might be far more difficult than optimistic projections suggest, creating natural barriers that keep most civilizations confined to their home star systems even after they achieve advanced technology. The challenges of interstellar travel are indeed formidable when examined carefully. The enormous distances between stars, the massive energy requirements for accelerating spacecraft to significant fractions of light speed, and the technical difficulties of maintaining complex systems across journeys lasting centuries or millennia might represent practical limits that few civilizations ever overcome. Even if interstellar travel is theoretically possible, the costs and risks might be so enormous that most species conclude that the benefits do not justify the enormous investments required. Similarly, the maintenance of galaxy-spanning civilizations might prove to be more difficult than theoretical analyses suggest. Managing social, political, and economic systems across multiple star systems separated by years or decades of communication delay could present coordination problems that become increasingly intractable as civilizations expand. Rather than continuing to grow indefinitely, most technological species might reach natural equilibrium states where they focus on optimizing life within a single star system rather than attempting the probably impossible task of governing a galactic empire. What makes these alternative explanations intellectually interesting is that they suggest radically different implications for humanity's future and responsibilities. If the zoo hypothesis is correct, then we are not alone in the universe, but are instead being carefully watched by benevolent guardians who will eventually make contact when we achieve sufficient maturity. If advanced civilizations typically turn inward, then our own future might lie not in conquering the galaxy, but in learning to find fulfillment through internal development and sustainable living within our own solar system. Yet even these alternative explanations struggle to account for the completeness of the cosmic silence we observe. While some civilizations might choose isolation, subtlety, or internal development, the sheer number of potentially habitable worlds and the vast spans of time available for evolution suggest that at least some species should have chosen different paths. If millions of civilizations have arisen throughout galactic history, statistical variation alone would ensure that many of them would be expansionistic, detectable, or interested in making contact with other forms of intelligence. The persistence of total silence across billions of years and countless potential sites for the development of life suggests that something more systematic than individual choices or technological limitations may be at work. While we must remain open to all possibilities, the Great Filter hypothesis continues to offer the most comprehensive explanation for why a universe that appears so suitable for life and intelligence remains so stubbornly quiet and seemingly empty of the civilizations that our best theories predict should exist in abundance. As we survey the landscape of potential existential risks that might constitute the Great Filter, from nuclear warfare to climate change to artificial intelligence, a disturbing pattern emerges that places our current historical moment in sharp and unsettling focus. For the first time in the 4 billion-year history of life on Earth, a single species has developed the capability to fundamentally alter or even end its own evolutionary story within the span of a few human lifetimes. What makes this realization particularly sobering is the recognition that we may be living through what philosophers and risk researchers call the precipice, a relatively brief but extraordinarily dangerous period in our civilization's development when we possess unprecedented power over our planet's future, but have not yet developed the wisdom, institutions, or global coordination necessary to wield that power safely. The concept of the precipice emerges from a stark temporal comparison that reveals just how compressed and critical our current era may be in the grand sweep of cosmic history. Behind us stretch approximately 4 billion years of biological evolution, during which countless generations of organisms lived, reproduced, and died, while gradually building the complexity that eventually gave rise to human intelligence. Ahead of us, if we successfully navigate the challenges we now face, lie potentially billions more years during which human civilization or its descendants might spread throughout the galaxy, exploring countless worlds and achieving forms of knowledge, creativity, and flourishing that we can barely begin to imagine. Yet sandwiched between these vast expanses of time lies a narrow window, perhaps just a few centuries, during which the fundamental trajectory of life on Earth and humanity's cosmic future will likely be determined. The decisions we make about nuclear weapons, climate change, artificial intelligence, biotechnology, and environmental stewardship over the next several generations may establish whether our species joins the extraordinary rare category of civilizations that successfully pass through the Great Filter, or becomes another silent testimony to the challenges that await technological intelligence in an indifferent universe. This temporal compression creates what might be called the paradox of pivotal centuries. After billions of years of gradual development, the most important choices in the history of terrestrial life are being made by people who are alive right now, using institutions and decision-making processes that evolved for managing the affairs of small tribal groups rather than global technological civilization. The cognitive biases, political systems, and social structures that served our ancestors well when their most dangerous technologies were stone axes and fire, now must somehow guide us through challenges that could determine the fate of billions of future generations. The convergence of multiple existential risks during this same narrow time window makes our situation even more precarious. Unlike previous generations, who might face one major challenge at a time, a plague, a war, or a natural disaster, we must simultaneously manage the risks posed by nuclear weapons, climate change, artificial intelligence, engineered pandemics, ecological collapse, and perhaps other threats we have not yet fully recognized or understood. Each of these challenges alone would represent a significant test of our species' wisdom and coordination. Together, they create a web of interconnected risks, where failure in one domain might cascade into failures in others. The psychological challenge of comprehending and responding to this convergence of risks is profound. Human minds evolved to focus on immediate, local threats that could be addressed through direct action, predators, rival tribes, food shortages, or natural disasters affecting specific communities. We are far less well equipped to process abstract, long-term, global risks that unfold over decades and require unprecedented levels of international cooperation to address effectively. The same cognitive biases that helped our ancestors survive in dangerous environments now make it difficult for us to maintain appropriate concern about climate change, nuclear proliferation, or artificial intelligence risks that might not manifest their worst effects for years or decades. This temporal mismatch between human psychology and the timescales on which existential risks operate creates what might be called the procrastination trap. Because these risks typically develop gradually and their worst effects may not be felt for years, there is a persistent temptation to delay difficult decisions and expensive preventive measures until the problems become more obviously urgent. But by the time existential risks become immediately apparent, it may be too late to prevent catastrophic outcomes. Nuclear winter becomes undeniable only after nuclear weapons have been used. Runaway climate change becomes obvious only after tipping points have been crossed, and misaligned artificial intelligence becomes a clear threat only after such systems have already been deployed. The institutional challenges are equally daunting. Managing existential risks requires forms of global coordination and long-term thinking that stretch far beyond the capabilities of existing political systems. Democratic governments face electoral cycles that reward politicians for delivering immediate benefits to voters, rather than investing in expensive insurance policies against unlikely but catastrophic future risks. International institutions struggle to enforce agreements when national interests conflict with global needs. Market economies excel at optimizing for short-term efficiency and growth, but provide few incentives for considering the long-term consequences of industrial activities or technological development. Yet these same institutional limitations occur at precisely the moment when the stakes of failure have become higher than ever before in human history. A mistake in nuclear policy could end modern civilization within hours. Poor choices about climate policy could set in motion changes that persist for centuries. Inadequate attention to artificial intelligence alignment could create risks that prove impossible to reverse once they manifest. The margin for error in managing these challenges appears to be shrinking, just as the consequences of error are reaching unprecedented levels. Perhaps most unsettling of all is the possibility that we are not unique in facing this predicament. If the great filter lies ahead of us, then countless other civilizations throughout galactic history may have reached similar points in their development, confronted with comparable convergences of existential risks and institutional inadequacies. The cosmic silence that surrounds us might reflect not the absence of intelligence in the universe, but rather a pattern of systematic failure that occurs when technological capabilities outpace the wisdom and coordination necessary to manage them safely. From this perspective, our current generation faces a responsibility that is both humbling and extraordinary. We may be among the first beings in our galaxy to clearly recognize the nature of the precipice and to understand what is at stake in successfully navigating it. The choices we make about global cooperation, risk management, and long-term thinking may determine not only the future of human civilization, but whether intelligence itself has a lasting place in our corner of the cosmos. We stand at a moment that has been 4 billion years in the making, facing decisions that could determine whether the next 4 billion years will witness the flourishing of consciousness among the stars or its quiet extinction on a small world orbiting an ordinary sun. When you contemplate the possibility that humanity might be among the extraordinarily rare civilizations capable of surviving the Great Filter, a profound question emerges that extends far beyond the technical challenges of managing existential risks or developing sustainable technologies. If we are indeed part of an almost impossibly unlikely success story in the cosmic drama of intelligence, what moral obligations does this place upon us, not just toward our own generation or our immediate descendants, but toward the vast multitudes of potential future beings whose very existence depends upon the choices we make today? This question leads us into territory that philosophers call long-termism, a moral framework that asks us to consider the welfare of future generations not as an afterthought to our current concerns, but as perhaps the most important consideration in how we structure our societies, allocate our resources, and make decisions about technology and global governance. The mathematical foundation of long-termist thinking is both simple and staggering. If humanity successfully navigates the Great Filter and becomes a long-lived spacefaring civilization, the number of people who might eventually exist could dwarf the current global population by factors of millions or billions. Consider the implications of this arithmetic across cosmic timescales. Our current global population of approximately 8 billion people represents the cumulative result of hundreds of thousands of years of human development, but this number becomes almost insignificant when compared to the potential populations of a mature galactic civilization. If humanity were to spread throughout the Milky Way over millions of years, establishing thriving communities around even a small fraction of the galaxy's hundreds of billions of stars, the total number of human lives that could eventually be lived might reach into the quintillions or beyond. Each of these potential future people would presumably have their own capacity for joy, creativity, love, discovery, and all the other experiences that make human life valuable and meaningful. They would write poetry and compose music, fall in love and raise children, make scientific discoveries and create works of art, experience the wonder of contemplating distant galaxies and the satisfaction of solving ancient mysteries. The aggregate amount of happiness, beauty, knowledge, and meaning that such a vast population might create over millions of years is literally beyond our ability to fully comprehend. Yet the existence of all these countless future generations depends crucially on decisions that we, their distant ancestors, make during the next few critical centuries. Our choices about nuclear proliferation, climate policy, artificial intelligence development, and international cooperation will determine whether this almost unimaginably rich future comes to pass, or whether the story of terrestrial intelligence ends with our current generation, leaving the universe once again silent and empty of conscious observers. This perspective transforms many familiar ethical questions in ways that can be both inspiring and uncomfortable. Traditional moral frameworks focus primarily on the welfare of people who currently exist or will exist in the near future, treating obligations to distant descendants as important but secondary considerations. Long-termist thinking inverts this priority structure, suggesting that because future generations could vastly outnumber present ones, their welfare should be our primary moral concern, even when it conflicts with immediate interests or desires. Applied to practical policy questions, this ethical framework suggests radical changes in how we approach everything from government budgeting to international relations to technological development. Instead of optimizing political and economic systems for short-term growth, employment, or electoral success, we might restructure them around the single overriding goal of ensuring that human civilization survives and thrives across cosmic timescales. This could mean accepting slower economic growth in exchange for greater environmental sustainability, investing enormous resources in reducing existential risks even when the probability of catastrophe seems small, and developing international institutions capable of coordinating human activities across centuries rather than mere decades. The long-termist perspective also suggests that some activities and values that seem peripheral to contemporary political discourse might actually represent civilization's most important priorities. Scientific research aimed at understanding and mitigating existential risks becomes not an academic luxury, but humanity's most urgent practical need. International cooperation and conflict resolution transform from diplomatic niceties into essential survival skills for a species attempting to coordinate its activities on a planetary scale. Environmental stewardship evolves from a concern about preserving natural beauty into a fundamental requirement for maintaining the stable planetary conditions that technological civilization depends upon. Perhaps most importantly, this ethical framework suggests that wisdom and moral development may be just as crucial as technological advancement for successfully passing through the Great Filter. A civilization that develops powerful technologies while retaining the tribal loyalties, short-term thinking, and zero-sum competitive instincts that characterized our hunter-gatherer ancestors might possess the capability to reach the stars, but lack the wisdom to use that capability safely. The same cognitive biases and social dynamics that helped small human groups survive in dangerous natural environments could prove catastrophically inadequate for managing global technological systems and existential risks. This creates what might be called the moral dimension of the Great Filter. Perhaps the barrier that stops most civilizations is not ultimately technological but ethical, the challenge of developing moral frameworks, social institutions, and decision-making processes sophisticated enough to handle the responsibilities that come with planetary-scale power. Species that solve the technical challenges of nuclear physics, genetic engineering, and artificial intelligence while failing to solve the moral challenges of cooperation, long-term thinking, and global governance might systematically destroy themselves not through malice, but through the application of Stone Age instincts to Space Age technologies. From this perspective, the development of ethical systems capable of caring appropriately about the far future becomes not an abstract philosophical exercise, but a concrete survival strategy for technological civilizations. Species that learn to value the welfare of their distant descendants, to coordinate their activities across global scales, and to make decisions based on their long-term consequences rather than immediate gratification might be the only ones capable of navigating the complex web of existential risks that await advanced societies. This ethical evolution might need to occur not just among political and intellectual elites, but throughout entire populations, becoming embedded in cultural values, educational systems, and social norms in ways that make long-term thinking as natural and automatic as the short-term survival instincts we inherited from our evolutionary past. The transformation required might be as profound as the transition from hunter-gatherer bands to agricultural societies, or from agricultural villages to industrial nations, changes that required not just new technologies, but fundamental shifts in how people understood their relationships to each other and their responsibilities to future generations. If we are indeed living at a pivotal moment in the history of intelligence in the universe, then developing these new forms of ethical thinking may be among the most important contributions our generation can make to the cosmic future. We may be called upon not just to solve immediate technical problems, but to become the kind of moral beings worthy of inheriting the stars and capable of ensuring that consciousness has a lasting place in the vast expanse of space and time. As we near the end of our journey through the landscape of existential risks and cosmic possibilities, we arrive at a profound fork in the road of human understanding that leads to two radically different visions of our place in the universe. Each vision carries with it vastly different implications for what it means to be human, what responsibilities we bear, and how we should understand the significance of our choices during these critical centuries. The remarkable thing about these two scenarios is that despite leading to opposite conclusions about the nature of cosmic life, both point toward the same overwhelming sense of responsibility and the same urgent need for wisdom, cooperation, and long-term thinking. In the first scenario, we are genuinely rare, perhaps even unique, in the observable universe. The Great Filter lies primarily behind us, embedded in the long chain of evolutionary improbabilities that we have somehow managed to navigate successfully over the past 4 billion years. The origin of life itself may have been far more difficult than Earth's rapid biological emergence suggests, requiring precisely the right combination of chemical conditions, energy sources, and molecular accidents that occur perhaps once in a trillion worlds. The transition to complex cells with nuclei and organelles may have been so improbable that it succeeded only on Earth, leaving countless other worlds forever locked in microbial simplicity. The evolution of multicellularity, the development of intelligence, and the emergence of technological civilization may each have required such specific sequences of unlikely events that our planet represents a cosmic miracle of almost impossible rarity. If this vision proves correct, then you and every other person alive today are part of something far more precious than we typically imagine. Humanity would not simply be one intelligent species among many scattered throughout the galaxy, but rather the universe's only known way of understanding itself. We would be the cosmos made conscious, the only observers capable of contemplating the beauty of distant nebulae, the only minds capable of discovering the laws of physics, the only hearts capable of feeling wonder at the sight of Saturn's rings or the dance of binary stars. In this scenario, our survival becomes not just important to us, but important to the universe itself, because without us, all the beauty and complexity that surrounds us would exist without any consciousness to appreciate it or comprehend its meaning. This perspective places an almost unbearable weight of cosmic responsibility upon our shoulders. If we are alone, then our extinction would represent not just the end of human civilization, but the end of awareness itself in our corner of the universe. Every scientific discovery that goes unmade, every work of art that goes uncreated, every moment of love and wonder that goes unexperienced because we fail to navigate the great filter would represent an irreplaceable loss not just to humanity, but to the cosmos as a whole. The stakes of our current choices become literally universal in scope, because we may be carrying the only torch of consciousness in a vast and otherwise unconscious expanse of space and time. Yet the alternative scenario carries implications that are equally profound and perhaps even more challenging. In this second vision, we are not rare at all. The universe may teem with life and intelligence, with millions of worlds where chemistry gave rise to biology, where simple organisms evolved into complex ecosystems, where intelligence emerged and eventually developed technology. But in this populated cosmos, most civilizations follow a familiar and tragic pattern. They flourish briefly before encountering existential risks of their own making, typically during the critical transition period when they possess global destructive power but lack the wisdom and institutions necessary to manage that power safely. If this interpretation is correct, then the silence we observe in the cosmos becomes not evidence of our uniqueness, but a warning about our future. Every empty star system might once have hosted a thriving technological civilization that lasted a few centuries, or millennia before succumbing to nuclear warfare, environmental collapse, misaligned artificial intelligence, or some other convergent risk that we have not yet fully recognized. The galaxy might be filled with the archaeological remains of failed societies, worlds whose atmospheres still bear the chemical signatures of industrial pollution from civilizations that ended thousands of years ago, whose orbits contain the debris of space programs that never reached maturity. In this scenario, our task becomes not to preserve the universe's only flame of consciousness, but to become one of the extraordinarily rare civilizations that learns to endure, to develop the wisdom and cooperation necessary to pass through the dangerous bottleneck that has claimed countless others. We would be called upon not just to survive, but to demonstrate that survival is possible, to become living proof that technological civilizations can overcome their own destructive tendencies and achieve the stability necessary for long-term growth and exploration. The profound realization that emerges from contemplating both scenarios is that regardless of which proves correct, our responsibilities remain immense and our current moment in history remains pivotal. Whether we are alone in the universe or surrounded by the ghosts of failed civilizations, the choices we make about nuclear weapons, climate change, artificial intelligence, and global cooperation will determine outcomes that matter on cosmic scales. Whether we are preserving the only known instance of consciousness or demonstrating that conscious beings can learn to survive their own power, we are engaged in work that extends far beyond immediate human concerns to touch the very question of whether intelligence has a lasting place in the universe. Both visions also suggest that our current generation may be uniquely positioned to influence these cosmic outcomes. If we are rare, then we are the inheritors of an almost impossibly unlikely evolutionary success story, and our failure to appreciate and preserve what we have inherited would represent a tragedy of universal proportions. If we are not rare, then we are living at precisely the moment when civilizations typically face their greatest test, and our success or failure will help determine whether consciousness proves to be a stable feature of cosmic evolution or merely a brief flicker in the vast darkness of space and time. Perhaps most importantly, both scenarios suggest that the work we must do to secure humanity's cosmic future is fundamentally the same, regardless of whether we are alone or surrounded by hidden neighbours. We must learn to cooperate across tribal and national boundaries, to make decisions based on their long-term rather than short-term consequences, to manage powerful technologies responsibly, and to create institutions capable of coordinating human activities on planetary scales across centuries rather than merely decades, whether we are lighting the universe's only flame or demonstrating that flames can be kept burning. The task requires the same transformation in how we understand our responsibilities to each other and to the future. As we reach the end of our journey through the landscape of cosmic silence and existential possibility, it is time to return to the image that began our exploration. A quiet galaxy, its hundreds of billions of stars scattered like distant campfires across the vast, dark plane of space, each one burning steadily through the cosmic night, yet none accompanied by the signals, the lights, or the unmistakable signatures of technological civilization that our theories predict should illuminate the darkness. This silence, which first struck us as mysterious and perhaps even ominous, now reveals itself to be something far more profound and complex than we initially understood. The quiet that surrounds us is not merely an absence, not simply a void waiting to be filled by the radio chatter and industrial pollution of expanding civilizations. Instead, it has become a kind of cosmic invitation, extended across the light years to any species wise enough to recognize its meaning and brave enough to accept its challenge. It is an invitation to learn, to grow, to become the kind of civilization that deserves to inherit the stars, rather than simply the kind that possesses the technical capability to reach them. The silence asks us whether we can develop not just the knowledge to build spacecraft and harness stellar energy, but the wisdom to use such power responsibly across millions of years of cosmic time. This invitation extends beyond the grand challenges of interstellar travel and galactic colonization to encompass the most intimate aspects of how we live our daily lives here on Earth. When you understand that our planet may be among the extraordinarily rare worlds where complex intelligence has emerged, when you grasp that our current moment may represent one of the most pivotal periods in the 4 billion year story of terrestrial life, every ordinary day becomes infused with extraordinary significance. Your morning coffee occurs against a backdrop of cosmic improbability. Your conversations with friends and family take place within a context of universal responsibility. Your work, your choices, your small acts of kindness and cooperation become part of a story that extends from the first spark of life in ancient oceans to the potential future spread of consciousness throughout the galaxy. Knowledge of the Great Filter transforms our understanding of what it means to live a meaningful life in ways that are both humbling and inspiring. Each effort to reduce conflict, each investment in education and scientific research, each act of environmental stewardship, each attempt to build bridges across cultural and national divides becomes part of humanity's collective effort to prove that technological civilizations can learn to manage their own power wisely. The teacher who inspires a student to pursue science, the diplomat who prevents a conflict from escalating, the engineer who designs safer systems, the artist who helps people understand their connection to the larger cosmos, all are contributing to our species' attempt to navigate successfully through whatever components of the Great Filter may still lie ahead. This perspective offers a new way of understanding the relationship between individual human lives and cosmic significance. You need not discover new laws of physics or invent revolutionary technologies to participate meaningfully in the most important project in the history of terrestrial intelligence. Simply by choosing cooperation over conflict, long-term thinking over short-term gratification, and wisdom over mere cleverness, you contribute to the great work of proving that consciousness can be a stable and enduring feature of the universe, rather than a brief accident that quickly destroys itself. The silence of the cosmos, viewed through this lens, becomes not a source of loneliness or cosmic pessimism, but rather a profound reminder of how precious and unlikely our current moment truly is. We exist during what may be the most critical centuries in the history of intelligence on Earth, when the fundamental trajectory of life itself hangs in the balance. Yet we also exist during a time of unprecedented human capability, when we possess both the knowledge to understand these challenges and the potential tools to address them successfully. Perhaps most remarkably of all, we may be among the first beings in our galaxy to clearly recognize the nature of the test we face and to understand what is at stake in our success or failure. Previous generations of humans lived their entire lives without knowing that they were part of a possibly unique experiment in cosmic intelligence, without understanding that their choices might echo across millions of years of future development. We have been given the extraordinary gift and terrible burden of cosmic awareness, of knowing that we are not simply another generation in an endless human story, but potentially among the most important generations in the entire history of consciousness in the universe. This awareness brings with it a form of cosmic humility that can be both overwhelming and deeply comforting. We may be early in the universe's long story, among the first civilizations to emerge in a cosmos that will continue evolving for billions of years to come. We may be rare, representing one of the few worlds where the unlikely process of biological and cultural evolution has produced beings capable of contemplating their own cosmic significance. We may be precarious, balanced on the knife's edge between transcendence and extinction, our future hanging on decisions that we must make without perfect knowledge of their consequences. Yet despite all these uncertainties, despite the magnitude of the challenges we face and the weight of the responsibilities we bear, there remains one fact that shines through all our cosmic speculation with perfect clarity. We are here. Against all odds, through 4 billion years of evolutionary accidents and near misses, through countless potential extinction events and seemingly impossible transitions, consciousness has emerged on this small world orbiting an ordinary star. Intelligence has learned to contemplate intelligence, life has developed the capacity to understand life, and the universe has produced observers capable of appreciating its own beauty and complexity. Somewhere, on a small planet in an unremarkable solar system, a young civilization has just discovered that there may be a great filter waiting in its future or hidden in its past. This civilization does not yet know whether it should feel gratitude for having won an impossible evolutionary lottery or fear at approaching a test that may have claimed every other technological species in galactic history. But it understands finally and fully that its future is not predetermined by the laws of physics or written in the configurations of distant stars. Instead, that future will be determined by the choices it makes, here and now, on this one fragile world that may be the only place in the universe where such choices are possible. The cosmos waits, patient and silent to see what we will decide.